are, by my count, ready to start. We'll be, even though we're very crushed for time, we got so much, what I think is maybe the most interesting content as we're building to it, stuff to cover. We are going to be nice. We'll give people another 30 seconds or so. And then we'll get started. I didn't see that many questions accrue, actually really none that I didn't address before I left for my lunch break. So we didn't have a stack there, so I didn't come back online live early to address anything. Okay, well, let's go ahead and get started then. This afternoon, we are going to do deep learning approaches and neural net approaches to machine learning. We'll revisit some of the topics that we looked at earlier. We'll find a lot of the themes that we developed starting yesterday and really coming on stronger this morning will be very relevant to what we're going to do with deep learning. I mean, this should be encouraging to you to know that there are a lot of underlying principles that if you understand them, you can apply across the entire field. It's always nice to have unifying principles instead of a mass collection of trivia, which is what this stuff can first seem like when you begin to learn it. One thing I think you're all aware of, probably a motivating factor for many of you, is that deep learning and neural nets, which again, things are synonymous. So as I flip back and forth between the terms, please don't be confused, have become really the forefront of not just machine learning, but many areas of science. And it's just astounding because it's happened so quickly. 10 years ago, if you'd thought the notion of modeling, say, multi-phase physics and chemistry with neural nets was a useful thing to do, it would have seemed laughable or science fiction-y. Now it's exactly the case. We'll step through many applications this afternoon. But the reason that this has happened is the widespread availability of two things, one of which are GPUs, the other of which are big trained data sets. And we'll see why these two pieces are so essential as we step through the actual mechanics and details of doing deep learning, which we'll do. But really, it's only because GPUs as part of computing became something that you could find in the average working scientist's workstation, about less than 15 years ago. And it's only because big data training sets, and big being, as we know from yesterday, a relative term, but meaning that we have at least tens of thousands of samples to train things on, have become so common across so many different domains that we've made these great leaps forward. So let's look at how these things work, and it'll be clear how those two pieces of the recipe are both critical and common these days. There are two ways that you can view deep learning that are typically taken up by most people. Either you can look at this as it's inspired by biological models. We look at how brains work. We look at how a slice of a human or any animal brain looks under a microscope, and you go, hey, we've got a bunch of neurons connected by synapses. Or you could look at it as we've got these classical machine learning techniques that started back in the 50s, and they've evolved, and this was just one of the end routes that they could have taken. It's one that's become suddenly very effective at a lot of problems. And they're both fair, and they're not contradictory. If we look at things as biologically inspired, and by the way, this continues to be an inspiration. Once we look at the details of neural nets work and we expand out to variants of these, you'll see that common new architectures and advances and even hardware is often inspired by the desire to emulate further the way nature does things. But at the simplest level, again, if you look at a slice of a brain, you see that there are these neurons connect to each other by synapses, and the synapses seem to grow and shrink depending on what corresponds seemingly to learning, perhaps memory. And if you decided you wanted to model those on a computer, you'd find yourself drawing a network. And as you got more and more realistic, the network would get very deep and very wide and have lots of these connections between things. And one way that you would, the most natural way perhaps to represent any sequence of connections in this network would be a matrix showing you the links between any given neuron and any other given neuron. And so you'd find yourself working with a big matrix of weights and looking at signals propagating through these as putting a vector into the matrix and seeing what comes out the other side. It's just kind of the most natural way to model these. By the same token, if you started out with a very, very simple classification system, the perceptron, that was first really discussed widely in the 60s and dismissed by the early 70s as hopelessly inadequate for doing things. The perceptron seems to be the precursor to modern neural nets in that in an attempt to classify objects, in this case, maybe cats and dogs, you want to distinguish between cats and dogs. You want to find some kind of space way of representing them where you can draw a line, a clear line between these two classes. And with the perceptron, it seemed that there were limitations to it. It couldn't represent certain types of logical operations, and people. There was one famous paper that managed to persuade everybody that this was just a dead-end technique and shouldn't be pursued further. And consequently, people kind of abandoned this approach for a good while. It took a while for people to recognize that not only was that paper mistaken in some senses, but that progress was being made regardless of the theoretically perceived limitations. And so if we look at this classification idea, we see immediately that one of the problems with trying to divide things up with linear classifications is that we've got data sets that are inherently nonlinear. You know, we're dealing with the world where things have a lot of curves and shapes to them that aren't amenable to nice linear separations between them. We have problems. One of the things that our neural networks can do with their hidden layers and their nonlinear activation functions, both things that we're going to jump right into in a moment. So don't worry if those aren't immediately obvious what we mean by that. One of the things we can do with these capabilities, though, is that we can warp our data spaces in nonlinear ways, like a rubber sheet, so that now when we've got classes that do seem to be entangled like this, we can draw clear lines between them. We can separate things. And so they are very good at, in this case, classifying things. So both of these, again, approaches are true and useful, and you shouldn't think that they're inconsistent with each other. And they both end up resulting in basic neural net architecture that looks kind of like this at the lowest level. We're going to work our way through exactly precisely how a neural net works, because there's nothing about it that's the least bit intimidating mathematically. It is very straightforward algebra to get from an input layer to an output layer of a neural net. So there's no reason not to understand that it doesn't need to be a black box. As we get towards the more higher level layers, what we're going to do with Keras and TensorFlow, we'll find that we can, with a few lines of code, construct very large and complex and sophisticated neural nets. But it's important to not think that the lower level pieces that we're shuffling around are difficult to understand. They are not. They are very straightforward. So let's look at this. A basic neural net architecture looks like an input layer where we throw some kind of data at it, and we'll look at varieties of data that we might have. We have an output layer where we get our results at, and that might be various kinds of things from a picture to a classification of something, dog or cat. And in between, we have layers. They're called hidden layers because they're not exposed to the world as inputs or outputs, but the hidden layers do most of the crunching and computation, and they can have various widths to them. In this case, 3 pixels. They can have various numbers of layers. In this case, with 1 layer. But the mathematics from one layer to the next are very straightforward. Now, in practice, what we actually have is, as I said, on the input side, we can have many different types of data. For example, you might have it be an image. If we have an image that we're inputting on the input side, typically each one of these neurons is going to be a pixel of that image. And if it's a color image, you might have 3 of them, one for each of the RGB channels, for example. So that's what an input side looks like for a picture. Could be an audio waves, could be lots of different things. And we'll look at lots of those different things. On the output side, and after you go through many layers, and how many layers can we have? Well, hundreds of layers are viable these days. On the output side, you might have something that's transformed into, in the case of something like a deep dream transformation, you might have an entire new image. Or in the case of something that's trying to segment a picture for a car to drive, you have an output image that says what the sidewalk is and what the street is and what a pedestrian is. Or it could be a bunch of classification possibilities. Say this is a dog or a cat or whatnot. So we have lots of varieties of inputs and outputs, and we'll go through most of the interesting categories as we look at these things. But that's the basic idea. Now, what's the basic math that goes on inside of the neural net? Again, it's extremely simple mathematics. It basically says to get from one layer to the next, all we're ever doing is, well, to get a tiny bit ahead of myself, we're doing some adds, some multiplies, and finally a little function on the end. It's nonlinear in some way. So let's step through this. Let's do the adds first. So in order to get the value that we're going to find at this neuron derived from the input layer. We have connections to all the neurons in the previous input layer. And each one of those connections has a weight that says how strongly each neuron is connected to the previous layer. And those weights are adjusted as the network learns. Those weights are what really give the network its knowledge. All the knowledge and learning in the model are embedded in these weights. But assuming that this network has learned to do something and it has these particular weights, we can figure out the value that this neuron here will achieve by saying, okay, we have these inputs going into it, and we have these three weights connected to these inputs. So the weights here represented for H1 will be 1 for this first connection, -2 for this next connection, and 2 for this connection. And the way that likewise, we have weights for the next layer here too. So we have weights to connect, say, O2 to the previous layer. O2 would have 0 connection to here, and it has 1 is the weight here, and 2 is the weight here. So these are what the weights represent. The way that the mathematics work at the end of propagating numbers through here, and we'll propagate some numbers through here, we'll see it in action, is that we have an activation function that's got to be nonlinear to do something useful. So this activation function that we involve in our mathematics is actually what makes this thing much more interesting than many of the previous classic machine learning techniques that lived in the world of linear mathematics. Linear mathematics is wonderful because it's very well understood, and there's lots of mathematical techniques that work well there, whereas nonlinear mathematics is always more complicated. It has been for hundreds of years. If you've got nonlinear differential equations, you throw up your hands right away and say, oh, we got very few analytical insights into this. If you've got linear differential equations, you have books and books and books of ways to visualize the inner workings of those equations. So the nonlinear stuff was undesirable for a long time, but it turns out that the nonlinear stuff gives us an awful lot of power. What are the nonlinear functions that we use in machine learning? They're very simple. There are only a handful of them that are popular at any point in time, and they shift in popularity over the years as people find more effective ones. And traditionally, the big ones over the years have been a sigmoid function, which is just a nice smooth function that looks like this, that constrains all of our output values from a range of 0 to 1. It's nice to have on neurons because it's nice to be able to say our outputs, have a limited range and whatnot. So for a long time, the sigmoid function was the nonlinear function we involve in our mathematics. However, over the past decade, since actually about 2012 is really kind of the breakthrough for it, it's become much more popular to use a function it's kind of simple-minded looking, called the rectified linear activation function. We'll see ReLU, or rectified linear unit, used as the abbreviation for a lot today as we do things. And the rectified linear function is this blue line right here. It's a very simple function. It just says anything less than 0 is 0, and anything greater than 0 is just whatever it is, a linear function. And this seems really simple. It has a lot less desirable characteristics about being smooth, et cetera, et cetera. But on the other hand, it's also really efficient to calculate. You can see doing the mathematics for this is extremely simple. And it works just great. It turns out in one of those empirical things where people start trying it, they find out that this works really well. And by the way, some of you may be saying, how is this a nonlinear function? It's made up of 2 lines. Well, anything that's not a single line is nonlinear. Anytime you've got an if-then in this case, if I'm less than 0, I'm 0. If I'm greater than 0, I'm not. Anytime you've got an if-then in your logic, you're doing some nonlinear logic. So this is a nonlinear function, even though it looks like pretty linear, but pretty linear is still nonlinear. So this is our nonlinear function. We're going to roll into our mathematics in just a second as we jump into those mathematics. Here's what the mathematics look like. So here's the full math, starting out from the beginning of a network to the end. So let's look at this neural net neuron right here. It's going to take the input values at each of its 3 input neurons, 0.5, multiply that value by its particular weight of 1. It's going to take 0.9, multiply it by its particular connectivity weight of -2. And finally, -3 multiplied by its weight of 2. And here's the mathematics for that. It's just this sequence right here. Then at the end, we apply our nonlinear function. And if we choose the sigmoid function for our nonlinear function, we get something like this. We get 0.13 here. So this is the entire mathematics to get from one layer to at least one neuron in the next layer. The other neurons are doing the exact same thing with their own sets of weights. So this is very straightforward. And there should be, I hope for none of you, no confusion as to what's going on here. We could teach anybody that knows arithmetic how to pump things through here, assuming they know how to look up the sigmoid function. So we're pumping things through this network. Very simple, straightforward mathematics. Now, as we do this, oh, by the way, here's the mathematics for the last output layer. Nothing surprising here. So we've got the find value 0.35 here. We just work from the previous layer and its own special weights and the values that are existing here in the deep layer, the middle layer. So this is very simple, straightforward mathematics. Now, the second you start doing this stuff, you notice that you're really with the weights, you're working with a nice matrix here. Nice, look at this, it's one step from being a matrix. And with our inputs that we have coming in to each one of the input neurons, looks an awful lot like a vector. And as a matter of fact, the mathematics that we're performing here are exactly like multiplying a vector times a matrix. So here once again comes the most basic linear algebra kind of operations, multiplying a vector times a matrix. It's mostly what we do when we do machine learning. We do lots of vector matrix multiplies. And so we can represent this stuff as these linear operations very easily when we're done. And we have our output vector, vector times a matrix gives us an output vector. We apply the sigmoid function to each one of the components of that vector, and we have our final outputs from that layer. So this is very straightforward, simple linear algebra. And as a matter of fact, this looks an awful lot like the kind of things that you pump through a GPU. If you know anything about GPUs, and I'm not assuming you do, but if you came to, say, our OpenACC GPU programming course, the first thing you learn is that GPUs are fantastic at doing a lot of matrix multiplies. That's what they do. That goes back to the roots as being video cards and pumping out lots of pixels on a screen of when you're playing Doom at 140 frames per second. So this is what GPUs are great at. It's one of the reasons GPUs were a key component of revolutionizing deep learning, is that deep learning had always been trying to do a lot of this, and along comes a device that on your desktop can do these days, dozens of teraflops of these operations per second. So that teraflops there being how many trillions of operations you can do per second, cranking this through. Usually low precision. We'll come back to it later on, but these results are, started out being done on GPUs as 32-bit precision because, hey, that's generic floating point precision. These days, we find that the specialized hardware that we'll talk about later that's in the cards to do this works at largely 16-bit fixed point precision. And there are people doing very effective deep learning with 4-bit precision. 4-bit precision, that's absurdity, right? Not heard of anywhere else in computing. But it turns out that ends up being very efficient. We'll return to that topic later. One additional little piece of mathematics that's involved in this stuff is the fact that we find it useful when we're doing this deep learning to be able to kind of offset the outputs and inputs from one layer to the next by some shift, some general shift. You can think of this as it's nice to be able to either center our data around maybe our activation function so that it's most effective. You can think of it as it's nice to normalize inputs. If I'm staring at a bunch of images and I'm trying to learn things from them, if some of them are very dark and some of them are very bright, isn't it nicest if somebody color balances them all before they hand them to me so that they're all roughly the same color balance? Well, nets tend to learn with things that stay in that middle range. We'll come back to this in a more sophisticated function with batch normalization later, but at any rate, even your most basic neural nets have a bias that gets added in, typically one per layer, to all of our outputs. And so this is the full mathematics of a full neural net. Is we have our input vector, we multiply it by our matrix of weights, we apply our sigmoid function, or excuse me, we add our bias, and then we apply our sigmoid function, and we get our final outputs. That is the full mathematics of a neural net. And so you should be able to go and look at the most complex deep neural net and work your way through it, understanding exactly what's going on, even though it will be slightly tedious, well, terribly tedious to do. Okay, well, why is this nonlinear function in the loop? What does it add to the mix that is so revolutionary that all of our previous linear machine learning techniques couldn't do, that led us to believe that the perceptron and whatnot were just inherently very limited? The nonlinear function allows us to take our data space and give it some warps, some bends to it that aren't linear operations. And if we look at this animation in front of you right now, you see right at the end of the animation, there's this particular bending and warping of the transformation. That's the nonlinear function. All of the linear operations in the world can only give you skews and rotations and translations. They can't do this warping, this bending of the lines. So linear operations, again, if you're a linear algebra person, you can think of it as linear transformations. Coordinate transformations can't bend the lines. Maybe it's one of the benefits of them as a coordinate transformation, but a lot of times we need to bend the lines. We need to separate data sets in ways that we'll visualize a bit more. So this is a picture to keep in your head when you're trying to figure out what's going on with what's happening in these operations. The matrix multiply gives us a skew. That's the first operation that bends the lines or at angles to each other while they stay straight. It gives us rotations, and it can give us a scaling. The bias gives us a translation, but the activation function is at the very end what gives us a warp. And that's what allows us to do a lot more interesting things, because here's what we want to do with data sets. We've got a data set here on the left of some red and blue data that we want to separate into two classifications, two different categories. And on the left, we can see it happening as the network's learning how to do it. It's learning how to find the right weights to separate things. And eventually, it's able to tease these things apart so that we can draw a nice line here on this rubbery sheet between the two when it's finally done. So right about now, it's done, and we can draw a line here, and we can say these are cats and these are dogs very clearly. The one on the right is not successfully learning. It's trying to learn, but it's not getting there, and so it's never able to untangle the lines. But the fact that we can even attempt this and we can warp this sheet in such a manner is because of that nonlinear function at the end. Otherwise, all we could do is rotate the sheet and scale it up and down. Now, an additional thing, and these are things, by the way, that a lot of people that even have taken a semester of deep learning aren't really aware of, because you don't have to introduce these concepts. You can just crunch away at the numbers and do linear operations and never realize this. But I think it's extremely useful to understand what you're actually doing. And it's possible to do by understanding things at this higher level and how the mathematical operations actually result in geometrical type of operations. One of the things that you rarely see mentioned, even though I think it's extremely useful to grasp, is that the width of the network allows you, and again, you can drill into the mathematics, but or you can take my word for it. Mathematics aren't that complicated, but you can take my word for it, that the width of the network corresponds to how many dimensions you're actually working in, how many dimensions you're able to play around with the data in. And why is it useful to have a lot of dimensions? We've been talking a lot about dimensions and how they come into play over the past day and a half. Why is it useful to have higher dimensions? We've been trying to get things to the lower dimensions. For once here, we're going to see how working in higher dimensions can be useful. It's because if you have a data set that looks like this, the cats are represented by this kind of data, and the dogs are this kind of data. However we warp and twist this sheet in 2 dimensions, we're never going to be able to separate these two with a clear line between them, some kind of plane between them. It's not possible. However, what if we do it in 3 dimensions? What if our rubber sheet now, we move into 3 dimensions, and so we do what we're trying to do here on the left, and we start trying to push basically the middle, the red section of the sheet. We start trying to push that section through where the bullseye is so that we can draw, as we see in the middle here, a plane or a hyperplane. If we're in higher dimensions, we can draw some kind of nice line between the 2 categories. On the right here, we can see when it's finally succeeded, you can see you can draw a nice plane here between the red and the blue dots after it's succeeded. This, working in higher dimensions, gives us the ability to take problems which are intractable otherwise, like our 2-dimensional problem, and make them work out. As a matter of fact, how about this problem right here? If this is our data sets in 3 dimensions, seems like how we're going to have a hard time drawing a plane between these. But if we move into 4 dimensions, we'll find out that in 4-dimensional space, we can separate these 2 apart so we can draw a clear line between them. So again, hard to visualize things in 4 dimensions, but it's absolutely the case. It's this direct generalization of what we just did with 2 circles. And so this working in higher dimensions capability is, along with our nonlinear warping, gives us the ability to really tease apart virtually any data set. Now, theoretically, as a matter of fact, we can do anything. And so this is where you don't want to get too carried away, because people look at the universal approximation theorem, which says that even one hidden layer network of this type can approximate any function. And if you can approximate any function, that's a way of saying you can do anything, right? It means given some inputs, if I can do any function, I can have any outputs I want. So given my inputs of a bunch of pixels, I can make sure the function always figures out which ones are pedestrians and which ones are sidewalks from the image recognition. So,
John,
yes.
John, we've got 5 questions that are up if you want to look at the last 5.
Okay, let's take a pause here and get to these questions here. Okay, let's see.
Can Ariel, you do the same warping?
Yeah, let's see. I got it here. Let's see. First question here. Oops, we're scrolling away here. Does anybody know if RNN, LSTM, Muzzle resistance Spark? Well, we're going to come back to this, but probably you want to do these within TensorFlow like we're going to do here. Let's see. Spark session looks like this. Okay. You probably don't want to be playing along with these models in Spark for reasons that we'll get into as we get more practical here. It's possible, but it's not. Let me introduce how you would do that. Let's see, the 3 blue, 1 brown video somebody mentions, I will mention later on, that exact one in my slides. Let's see, can really do the same warping and bending like other nonlinear functions? Yeah, absolutely. Any reasonable nonlinear function can be stacked in such a way with the linear operations it can do just about anything, but ReLU, yes, can do anything. Theoretically, again, how practical it is at doing it is the interesting question. Width is in the number of nodes in one layer. Yes, width is the number in one single layer. That's width. Depth is how many layers, and width is how many nodes in one layer. Does the dimensionality be a problem? Then inform what you should use the width of the network. As a starting point, yes. But we'll find out that not as a really, really good endpoint. There's a lot of empirical things to know. But as a starting point, yes, you don't want to have the dimensionality of your network, at least on the input side, be less. It's really impossible to do that without doing something dumb. But we will find reasons we want to squeeze our dimensionality down and do dimensionality reduction on purpose. We want to go to lower dimensions. That can be useful in encoders. So we're going to jump into this subject in more depth. Is there a maximum number of dimensions? Well, however wide you can afford to make your network computationally. Let's see, neuroamine, we covered that. With this slide regarding the function, how does this relate to Fourier series approximation? Is this extend to higher dimensions? It's not really directly related to Fourier series approximation. So these are, well, Fourier series, you can view almost the entire world through the lens of doing Fourier series or orthogonal functions. It's a little bit of a stretch from here to there, so it's not particularly useful to relate the two. The universal approximation theorem, as I was saying, can be a little bit deceiving, and it makes it seem like, well, it's one layer can do anything, but it's not particularly actually useful. It's not a really practical way to view the world because the width can be enormous. As a matter of fact, the width can go up exponentially, typically, for any reasonable problem. So it's not a good way to deal with problems. Is make a network wider and wider. You're encouraged to experiment with that. We'll do some experiments along those lines. And also, one thing we haven't gotten to yet is how to actually find these weights. And so, how do we get these magic weights that do this magic smart stuff? And making a very wide network doesn't help us in that problem at all. So the universal approximation theorem is a good way to answer a lot of your theoretical questions. Dispense with them right away. Yes, we can do anything with a one-layer network. Reality, not really a good guide to getting things done. Okay, the question of how do we find these magic weights is very important practically. We've seen these networks teasing data apart and warping sheets. Well, how do we get there? And the answer is, and there's one of the commenters, well, I'll get to one of these comments in the next slide, I guess. The answer is that there are a variety of techniques on paper, but there's one that emerged in the 80s called backpropagation that is the only way that's used today in order to do this. And backpropagation basically says, if we look at the interrelationships between all of these weights and going from the input layer to the output layer, it really seems intractable. It really just seems impossible to figure out how they all adjust each other and everything to get you so that if I have an input of a picture of a dog, that I get a neuron that lights up and says dog instead of cat, because they're also interrelated. So how do we deal with it? Well, if instead we break the problem down a little bit and we say, okay, if this is the output layer here, and we know we're putting a picture of a dog in over here, and we know that we want the dog neuron, the one we said should learn to indicates there's a dog, to light up, to have a high value, maybe have a value of 1, while the others have a value of 0. We want it to have a value of 1 and the others have a value of 0. So we know that that's what we want. We put a picture of a dog in, though, and we get something else. So we put this picture of a dog in here. Let's say this is what we're dealing with. Put a picture of a dog in here. We've got our 3-pixel picture of a dog, but in reality, this is maybe hundreds and hundreds of pixels that give us our thousands or millions of pixels that come in with our picture of a dog. And we know we'd like dog to light up, but in reality, it looks like cat is lighting up stronger here. So we want to push these weights around and fix this a little bit. Well, again, if we look at the overall whole problem, it seems too daunting to even approach. But if we look at it instead from this last layer, so here's our last deep layer. And so our last deep, and we only have 3 layers here, but again, we could have many, many layers. And we look at our last deep layer and we say, okay, here's what's going in to making this 0.35 answer. And we know what we'd like to do. We'd like this number to go up, the output should be higher. We want this to go up to 1. And so we can see how these last layer, it has a weight here that connects it. And we have some values here in this intermediate layer here. So from this perspective here, if we want to figure out which way to push this particular weight, what we need is a function that tells us how the error depends upon the weight. If we have that error depending upon the weight function, that gradient there, that differential right there tells us which way to push the weight. And so we just need dE dW, the error with respect to the weight. And with many weights, so we're going to have many dE dWs here, and these are partial derivatives because we've got a function of many, many variables, but this is no more complicated than freshman calculus. You've got a partial derivative function here, and we know what the functions are involved because we can write these things out. We just got done doing the mathematics earlier on, saying here's how we pump things through here with our weights and our nonlinear function. And so we can figure out, you know, based on the sigmoid function, it's got a nice derivative. We can figure out the basic calculus here to say which way to push the weight and how much to push the weight. And so if we only had a network this big and I said, can we figure this out? You'd say, yeah, it's perfectly tractable. The problem becomes in that our networks are much, much bigger, could be dozens or hundreds of layers deep and very wide and have consequently millions, many millions, hundreds of millions of weights. And so that's where it looks impossible. Well, backpropagation comes to the rescue here and says that what if we treat each, well, I'll use the previous slide image for a second here because it makes it a little bit easier to see. Backpropagation says, what if we do this one layer at a time? We adjust all the weights here. It's not quite perfect because these weights are still going to depend on these other weights and whatnot, but let's try it that way. Let's work our way backwards one layer at a time and tweak all the weights. And eventually we'll be tweaking this one way back here. It's still got all these dependencies and everything, but these dependencies really just add together with, you know, with what we're doing from the previous layers. And so we can propagate backwards, work our network backwards from the input direction and tweak all the weights. It's not going to give us the answer in one pass, but if we keep doing that, if we keep doing backpropagation with new images, we're going to hopefully converge on the answer, or I should say an answer, because we're going to find out the perfect answer we won't get to. The reason we won't get to the perfect answer is because it's such a complicated problem. It's got so many variables. All we can hope for is an approximation. Now, this backpropagation method, I've just given you kind of a hand-waving overview of it. And that's because it would take me probably about 20 minutes to a half an hour to go through all the details of exactly which way you push one thing or another. However, several people, well, many people have given explanations of it, but there are several that are really fantastic. They go through it in about 25 minutes for you. So if all you remember is kind of calculus, kind of sort of, you're going to be fine with either one of these explanations here. There's a very elegant perspective on this. Chris Olah, who's got a fantastic blog on deep learning, machine learning, and he's got a particular article on backpropagation, explains it well. And for many of you, there is a fantastic math website. Guy does an incredible job of explaining math, usually visualized very well. 3 Blue, 1 Brown. And Sanderson does a fantastic job of explaining backpropagation in, I think it's about a 25-minute video. And you will absolutely understand exactly how it works at the end of that 25 minutes. I just don't have the 25 minutes to go into. And by the way, it's going to be a simple plugin in TensorFlow. You'll just assume that TensorFlow does all this for you. So many people never bother to learn backpropagation. They just they assume that the TensorFlow is doing the right thing. But if you care, you can learn it in precise detail in 25 minutes. Now, what backpropagation doesn't do for you, though, is solve all the equations. It gives you a bunch of equations back that you've got to solve. So backpropagation gives us back potentially many hundreds of millions of equations. And these equations, by the way, are nonlinear. And so we end up with a space that's convex. It's basically got lots of little dips in it, lots of local minimums. We want to find the lowest error. Error is at the bottom of this graph. Somewhere down at the bottom here is the smallest error we can achieve. But along the way, we've got many, many dips. And by the way, this is drawn in two dimensions of variables. So 2 variables versus error. But in reality, we have, as I said, hundreds of millions of variables. And so we've got hundreds of millions of dimensions, basically. And we've got a function that's complicated looking, and we're trying to find the very bottom of it. Well, we're not going to ever find that very bottom of it. Instead, we hope to find a decent local minimum, a good low error value. And it turns out that we can do that. It's extremely difficult to analyze analytically why that happens and how it happens and what your convergence criteria are. As a matter of fact, with the modern networks that we're going to look at, basically it's impossible. We throw up our hands and just have some hand waving guesses. But the bottom line is that we're trying to find a good local minimum, a good small amount of error. And good means that we don't take the first one we come to. So there are a lot of techniques as we're marching our way down this slope here with our solvers to say have something like momentum. Momentum says, as the name suggests, it comes from physics, that when we get to here, we might be say, let's pretend our marble has a little momentum and roll a little further and see if we can get this minimum instead. So we can do things like changing the step size, how much we go one step to the next. We can have some momentum. We can do a lot of different things, and we can change the step sizes as we go along. We can do a lot of different things, but at the end of the day, we're trying to solve such an incredibly complicated function that we're just going to approximate it. Now, lucky for us, this kind of situation is not unique to deep learning. This is true for, say, trying to solve a finite element analysis mesh if you're an engineer designing an airplane wing or a bicycle frame. And so the world of engineering has given us a lot of great tools to do this. The classic one, most widely used one by far, is to attack something like this with gradient descent, basically an algorithm that tries to figure out what the gradient, the slope is, and march down the slope, or march down the slope in some particular fashion. So gradient descent turns out to be a great way to deal with the equations that backpropagation hands us. Again, the details of gradient descent aren't that difficult if your math is pretty decent. But a lot of people treat it as an absolute black box, and TensorFlow allows us to treat it that way. That's fine. You don't need to be an expert in this to use it effectively. So we'll use a gradient descent or variations of it as we solve our equations today, and TensorFlow will make this trivial. Now, when we train, it's important to recognize, though, that what we don't do is show a picture of a dog and then adjust all the weights because it's off a little bit. Instead, what you'd like to do in the most elegant universe is show it all of your pictures of dogs and cats so that it has all the different input data, and then adjust all of the weights to minimize the error across that full set of training data. That's the most basic, straightforward way to do it. However, that takes a lot of time to go through all those training samples. We'll find out that we have at least tens of thousands and maybe millions of training samples, hopefully. And so you don't want to go through, in some sense, you do want to go through all those before you adjust the weights, but it's so expensive that instead a much more effective approach, at least empirically, turns out to be to go through some subset of those data. Show it a couple hundred pictures of cats and dogs and then tweak the weights a little bit, not the full set, then show it another couple hundred. Grab some random images out of that set and use those to train it and tweak the weights. Then by the time you go through the full set, which is an epoch, by the time you get through a full epoch of the set, you've already adjusted the weights a bunch of times. The size of those batches that you use to adjust it is called the mini batch. And that's a parameter, a hyperparameter we can adjust how big our mini batch is. So we use mini batches to adjust our weights. And eventually we go through mini batches. We've gone through a full epoch and we can say, okay, that's how many training cycles we've done, a full epoch. Now, this is called stochastic gradient descent because there's a little element of randomness to it. The stochastic bit is that we're not doing all the weights at once and picking the perfect adjustment. Instead, we're picking random samples and using that to adjust things, hence stochastic gradient descent. And again, the single slide that I've talked to death and without diving into the details is because most people will treat this as a black box. And I think that's a reasonable approach. You're perfectly capable, probably most of you, of understanding it by, reading, the Wikipedia page or whatever on it for an hour, but there's no need to be effective with it. Treat it as another solver for equations that's in a math library and you'll be good. Okay, we've got a lot of pieces here we've talked about, and we have all the pieces we need to start to do interesting things. So let's go ahead and start to do something. Now, if you want to play along with me in real time, you're allowed to. I would suggest more strongly than ever that you don't and pay attention because we've got a real flurry of material, an awful lot of stuff here to cover and new concepts. Please don't distract yourself unless you're really comfortable with, with working in this environment. And maybe you already know some of the material. Otherwise, pay attention and you can go back after and do everything you need to do. To do everything, to work through these exercises, and most of the interesting ones we're going to cover are sitting in your exercises directory. You want to be on a GPU node. As I mentioned, GPUs are really the vast majority of deep learning training and execution these days. There are some exceptions we'll talk about at the end, but by and large, most deep learning revolves around GPUs. So you want to get a GPU node. You'll know you're on a GPU node when instead of saying, being on a login node, it says GPU 46. Once you're on a GPU node, you want to load, we're going to do this in containers. We have modules on bridges to do this, but this is the latest, greatest version of TensorFlow. The most robust way to do this is to do it in a container. That's another way we can work on bridges. To load the Singularity container, make sure you load the Singularity module, and then load this particular container. Corresponds to exactly the TensorFlow version that we're using here today, which will be fine for all these exercises. And you'll find yourself sitting in a normal command line. If you type Python there, then you'll find yourself once again in a Python shell like we've been working in the past day and a half. Only all the TensorFlow stuff will be there. And TensorFlow likes to make a lot of noise when it starts up, when it runs your codes and what's not. I've edited that out of the slides just because who wants to stare at it, and it takes up valuable slide space. But don't be put off when you start up some TensorFlow stuff and it lets you know that the GPUs are there and they're working and etc. Okay, and once again, you can also execute these things from within the shell. You can run, say that, for example, the CNN Python script that we have for our convolutional neural network we're going to do later on. That's sitting there, and you can just run the whole thing straight off of out of the file if you'd like to. So the exercises are again, all the interesting ones are sitting there in your exercises directory. Now, as you do these things, you want to have the documentation open next to you. The documentation for TensorFlow is very nice. It's one of the reasons that I've chosen this framework for the class. It's also one of the reasons it's very, very popular. It's got really good documentation. We'll find ourselves using a lot of parameters and whatnot as we go along here. You absolutely want to have it open in the browser next to you. Okay, here's our problem.
A couple questions, John.
Okay. Okay, let's see. I'll jump on the questions here since the chat window is keeping up appropriately. Let's see. Question: how to avoid being trapped in a local minimum but jump out to find a real minimum? Okay, well, first of all, as I said, we're never going to find the actual real minimum in this space. It's just too large and complicated. We're going to give it up and never say we're finding the real minimum. And that's typical of lots of large complex problems like this where you use gradient descent. You just say, I'm going to find a good minimum. So we're not setting our goal so high as we're going to find the absolute true global minimum. That's just too much to ask for. We want to find a good minimum though. And the way that we try to keep from being trapped in the terrible local minimum. So we're going to be in a local minimum. We're not going to find a global minimum. But the way we try to stay from being trapped in a terrible local minimum are techniques like momentum, where we try to go a little bit further over the edge and explore the space a little bit more. Is this container kind of containerization technique like Docker? Yes, this is very much like Docker, except with higher security. So if you use Docker, you can convert a Docker container to a Singularity container. So if you use Docker containers don't have any good security in them. They're a terrible security hole. So you really don't want to use them on a shared system. And so on bridges and on most high performance computing platforms, and really any platform you're on that's supposed to be secure with multiple users, you want to use Singularity containers. You want to convert your Docker container to Singularity containers. And so that's what we've done. So these are Docker containers that are just converted to Singularity containers. Do you have any comments on PyTorch versus TensorFlow? Yes, I do. We'll get to those later on. But first, it's a lot more helpful for you to at least learn one of the frameworks before we compare them. So we'll continue. We'll teach you TensorFlow, and then we'll compare it to PyTorch. To not keep you in terrible suspense, PyTorch is similar to this in lots of ways. We're not going to do anything here you couldn't do in PyTorch. I think this is just slightly friendlier, but we'll come back to that later on. When you're done here, you'll be able to jump into PyTorch if you want to without a terrible amount of pain. Okay, so the problem that we're going to use here, we're going to leverage a lot out of. We're going to get a great amount of use out of this is MNIST character recognition. And this is a classic, very, very important problem. It's been used to benchmark countless different approaches and will continue to be used to benchmark different approaches. And it goes all the way back to the late 90s when it was first generated as a character set. Maybe it was responsible for starting the trend of having standardized data sets that we compare ourselves against competitively. It's certainly used that way. And the idea is that we've got these characters that are 28 by 28 grayscale images. So they're not super high res, but good enough. They're grayscale images. We've got 60,000 of them, and we've got 10,000 of them as a test set. So we've got to have a test and a training set of these characters, again, for the same reasons we needed test and training earlier today. So we've got test and training characters, and we're going to learn how to recognize these things pretty accurately. And TensorFlow makes it very, very easy to deal with a lot of these interesting test sets because it often has built-in data sets for some of the classic big test sets that are out there. So you're gonna have no problem downloading test set and MNIST as a test set. As a matter of fact, in our previous versions of the workshop, that's what we do. We go out and download our own copy of it, have it sitting in your directory. But instead, with modern TensorFlow, for some of these, they've built it in. So if you download TensorFlow yourself, you'll find that it's got this data set sitting around in its data sets. And so you can load them in yourself. And then it's very easy to look at exactly what they're doing here, how the data looks. As a matter of fact, I will have here, as we go through these examples, some simple matplotlib code. So if you're comfortable with matplotlib, if you're a Python user, I assume you're comfortable with matplotlib, since it's probably the most valuable tool to have in Python, up with NumPy. And I'm going to put some sample codes in there. If you're not a Python person, you can cut and paste these examples, and they use the graphics plotting library that's most popular with Python and allows us to do a little graphic stuff. I'm going to make these as sidebars in our code so they don't clutter up the code. So I won't actually stick these in the code, but if I were to just stick this little piece of code in right now, it would spit out a picture of one of these MNIST characters for us. And we can see that it's nothing more than an actual 28 by 28 array of grayscale imagery. So that's all this matplotlib code does here. It shows us the digit 4 looks like this. Each digit comes with a label. Now we're moving into the realm of supervised learning. And supervised learning is the most well understood and commonly done deep learning, which is where we train the network by showing it examples and telling it what the right answer is. So we showed a picture of a cat and we tell it this is a cat. That's how we adjust the weights. I showed you that earlier. I said we put a picture of a dog up and then we know that it's a dog, so we know which way to push the cat values. That's the supervised bit. If we just show up pictures of cats and dogs without labels, we wouldn't know which way to push things. So supervised learning says we have, for every data input we have a label. And this labeled data is where data gets to be expensive. I mentioned earlier, people sometimes get stingy about setting aside test data and screw themselves over that way. And the reason is because if you got to hand label all of your data, that can be expensive. So way back in the 90s, some poor graduate students, I assume, had to label 60, 70,000 characters by hand. And they did, and that's how we got this data set. Today, we've got people doing much more complicated things like labeling tumor outlines on x-rays to train radiology learning, deep learning that. So labeled data is sometimes expensive and painful to get, but it's how we do very effective supervised training. So in this case, our MNIST data set, every character image comes along with the appropriate label. So that's what we're getting here. We're getting our images and our labels out of the MNIST data set. So it's very easy to do with TensorFlow. Now we've got to massage our data into the right shape, though, for what we're about to do. In our case, we're going to throw our images, our 60,000 training images and our 10,000 test images, we're going to throw them at the input layer of a neural net. Now, the input layer of the neural net, as we've seen, is a bunch of neurons, right, that you throw pixels at. And so we need to take our image, our 28 by 28 images, and stretch them out into 784 pixels. And so that's what we do. We're going to turn our array, our 28 by 28 array, into a vector that's 784 pixels long. Now, you might say, aren't we losing some structure from the image? Doesn't the fact that the image is a 28 by 28 array help us to recognize it as a character? And instead, we're going to stretch it out as a big vector and look and use that. Aren't we losing something? And the answer is yes, we are. That is going to cost us in some way. We're going to come back later and see how convolutional techniques can take advantage of that structure. But we'll be able to do this basic approach and get some good results out of it by doing what you do with your most basic neural nets, which is stretch everything out into a single big vector. So that's what we're doing. We're going to take a single big 784 vector and throw it at our neural net, which is still to come down below. Now, we also actually have to do a tiny bit of conversion here. We need to turn these, MNIST comes to us as a bunch of 0 to 255 values, 1 byte grayscale values. We're going to find it's most convenient to work with neural nets when they have floating point values. And it's sometimes nice to start out with ones in a 0 to 1 kind of range, like treat things like they're kind of like probabilities. Not necessary. The network could learn to scale things. It would work if we didn't do this. You can experiment, but it's sometimes nice to at least try to give a thing a head start by normalizing our images. And so we're going to do that. We're going to make sure that what we end up feeding on below here, our test images, are going to be floating point numbers, and we divide by 255. So we're dividing our test images by 255 here, so that we end up with grayscale pixels with values between 0 and 1. So it's a nice way to make our images normalized in some sense. Not critical, but we'll do it. Okay, now's the fun part. Now is where we're actually doing some deep learning here. And this is where we're going to find out that the Keras layer of TensorFlow is incredibly friendly, very powerful. TensorFlow was originally developed mostly by Google, assuming that you were fairly sophisticated scientists willing to deal with all the low-level details, like having every layer of your neural net worrying about its matrix multiply and its bias, and what kind of activation function it had. And so it was a little bit long-winded in putting this stuff together. And as a matter of fact, before we're done, I'll show you a TensorFlow 1 code like we used in our earlier workshops. However, because there was a lot of boilerplate to it, it was tedious, somebody came along about 3-4 years ago, I guess at this point, and said, I'm going to write my own interface that sits on top of TensorFlow. It also sat on top of another library called Tiano. And it'll do this translation for me. It'll worry about the boilerplate code, make things friendly. And Keras became so popular because it is friendly that in TensorFlow 2, they decided to make it the default API. The default way of programming TensorFlow is now Keras. And so if you get confused by that, if you look at things, documents or literature from a couple of years ago, and you see Keras, that seemed to be a separate thing that used TensorFlow underneath. And now if you look at TensorFlow, it seems to have Keras embedded in it. That is indeed the case. We're going to benefit by that. We're going to use the Keras layer in TensorFlow. We'll look at dropping to a lower level before we're done very quickly, but there's not much benefit to it for you or for many people. So we're going to use the Keras interface to TensorFlow, and that will allow us to define a neural net this simply. It's extremely powerful. So let's look at what we've defined here. We've defined a sequential model, and that's what we're going to mostly use in TensorFlow, which says one layer feeds into the next. We'll see at the end that we can make more sophisticated networks with feedback and branching and things like that. But, and TensorFlow is happy to do that. It's not difficult. But for our sequential bunch of layers network, we'll just use the sequential model where we just give it one layer after the next and feed them in. And so what we're going to say here is we want our first layer of our network to be a 64 neuron network. Why did I want 64 neurons? Why not? A hyperparameter shows its head once again. Hyperparameters are no less important in neural nets, but no less, it's an understatement. They are very important in neural nets to pick the right architecture, sometimes seemingly out of a hat, most of the time with some guidance from what other people are doing, and always with the willingness to investigate and see if it's a good choice. So I'm picking 64 neurons here because it looked like it worked kind of sort of for somebody else maybe. And we'll play around with this number too. It's very painless to play around with it in Keras. I'm going to have 64 neurons in my first layer. And all I need to do is point it at the input layer, the inputs that are coming into it. So we're going to say that we've got an input shape here of 784 because that's the size of our vector. That's how many pixels we have in our input images. So we've got an input of 784. And we're going to have 64 neurons in that layer. Our next layer, because we're going to have a hidden layer in here, our next layer is going to have 64 more neurons too. So we've got another hidden layer in here. And by the way, we're defining our activation function in here as a ReLU unit, right? This rectified linear unit. So we've got two layers of 64 neurons. And then our output layer, we've got to define. Our output layer kind of picks itself, its own size for us. We have 10 digits. We better have 10 neurons on the output layer because each neuron is going to light up corresponding to the input digit. So we need 10 neurons on the output layer. So here's our full neural network completely defined. Our activation function on the output side is going to be Softmax. We'll come back to this in a moment. That's a nice activation function to have on an output side whenever you've got distinct categories that you'd like to have look like probabilities. We'll look at that in a little more detail, but it's just a nice output type for category layers on the output side. So here's our full neural network. And you can see it's very terse and compact notation. And it's very easy, I hope, for you, even though this is the first time you've ever stared at this, to understand what we've got going on here. We've got two layers of 64 neurons and a layer, an output layer of 10 neurons. Okay, so we're starting from 0 here, which means you say, as we point our down below the next couple of lines, we're about to tell this thing to use back propagation and to use an optimizer like stochastic gradient descent. So one of the things you'll find if you start worrying about looking at the math there is we can't have everything equal to 0. It won't get off the ground. If all of our neurons are equal to 0, there's no gradients, nothing to even approximate by. If we feed in a picture of a dog, nothing will come out at the end. So we can't have 0. We have to set these things equal to some value. So you might say, okay, I'll set them all equal to 1. Will that work? Well, that won't work because if we think about it, if it's one, everything's symmetric. All the neurons are going to see the same value from the previous. All the neurons are going to learn the same thing. They're not going to learn different stuff, so that can't work. We need some kind of actual random values in there. So we need to pick some random values to get the thing off the ground. Once again, random values just always making their appearance in machine learning. And so what random values should we pick? What should their range and their, what should their standard deviation look like? And the answer is we don't know from, we're going to pull something out of a hat, or we can look at what other people use successfully. And it looks like, maybe a standard deviation of 0.1 might work well or whatever. That happens to be the default that's in here. So we won't have to pick that. But if we wanted to, there's an optional parameter in here that allows us to pick our standard deviation or our mean for that matter for the variables that come in here. So they got to be initialized, and TensorFlow takes care of that for us. But it's an important thing to recognize it's happening there in the background. And again, you'll never pin it down analytically what exactly our initialization value should be. You really just want to kind of pick some reasonable values, or some fuzzy version of reasonable. But that's what's happening in the background. It's not, TensorFlow takes care of it, so it's, you don't see it, but it's important to recognize that's what's happening. Okay, now we've got a model that's defined architecturally wise here. Now we need to tell it, the last piece of the puzzle we need to tell it is what optimizer to use. And in our case, we're going to use a variant of stochastic gradient descent called Atom. It's an adaptive version of stochastic gradient descent, means that it's got an adaptive step size. So the step size for it can vary as it runs. Sometimes you want large steps, sometimes you want small steps. And it also has momentum. So Atom is a nice sort of acronym for that. So it's an adaptive stochastic gradient descent with momentum. And we can plug it in as simple as this. And we have other optimizers, like we could stick in class 6 stochastic gradient descent, just swap it in. So that's why we can treat this as a black box, and TensorFlow will do the right thing. Now we still have to make a couple more choices here. One of the well, we have to make one big choice. It's the last choice, and that is to define our loss. Once again, you don't know how well you're doing at picking weights or anything else unless you can say how badly you're missing, right? And as I said, if we've got cats and dogs and whatnot, and we have a picture of a cat and a dog shows up instead, how do we define that loss? We need some way to come up with a number. And the one we're going to use is called cross entropy. And it's probably it's absolutely the most common for categorical things. It's sparse categorical cross entropy. That's basically telling us we've got categories coming into this, and there's only one right category at the end, because we're going to pick one digit out of 10. So that's this part, but pretty much cross entropy is what you'll generically hear this referred to. We'll look at cross entropy in just a moment here. But first, I'll point out to you that we can investigate exactly what this model looks like at any point in time if we wonder what we've built by looking at the model summary after we've compiled it. So after you compile your model, if you wonder what you've just done, because this is very simple, but sometimes you can have lots and lots of layers, and you can be doing complicated things in layers. We'll work our way up to that. If you wonder at any point in time what you've got going on, you can just type model summary after you compiled it, and you'll get a nice little simple output here of exactly what your model looks like. In this case, we've got a first dense layer that's got 50,000 parameters. That's the number of weights that we have here if we look at 784 times 64. Our next dense layer is going from our 64 to our 64. So it's going to have 4160. Our last one is going down to our output layer. It's got 650. So these are the number of parameters that we have in our layers here. This is a nice summary of it. So our particular little neural net we just built has 55,000 weights to it, or parameters that it has to learn. There are no we'll see non-trainable parameters or things, well, they're the exception. We'll get to them later on. We have a few exotic networks. But in general, the total number of parameters gives you some idea of how computationally intense your network is. This is a pretty tiny network. This will fit on a GPU just fine, because we'll get up to, see hundreds of millions of weights for, current production kind of networks. So this is our model, but now let's look at what cross entropy, loss, and softmax are, because these are a couple of things that we've rolled into this network that I've glossed over, but there's no need to gloss over them. You can understand it. Well,
John, a couple questions popped up.
Okay, let's see what we got here.
Plenty of parameters.
No, we are not. So are we trying to have some kind of strategy? Basically, questions. We have some kind of strategy to limit the number of weights and biases that we have, because we don't. One of the things that would cause overtraining, overfitting of our data is if you have more parameters than you have data. that's going to encourage overfitting. So we don't want that. On the other hand, more parameters means a bigger, smarter network. So we do want that. So there's a little bit of tension right there. And that is where we're not going to have any really good strategy to give us. There isn't a good strategy to say how many we should have, because it turns out in real complex applications like we're getting into now, that tension is not easy to quantify. So how much you scale up a network is an open research question. And it turns out there's very different very different network sizes and architectures for different problems. So we don't have, even though intuitively we think we have some good guidance, I don't want to have more parameters than I need, because that'll make it easy to overfit the data. On the other hand, I see many examples where we have these extremely deep networks that do really well at certain problems. So your concern is valid. Unfortunately, we're going to find ourselves in the world of empirical investigation dictating really which way we go. And we'll find some networks that are fantastic with an extreme number of weights that manage to avoid overfitting the data. And we'll see some regularization techniques that we can help to deal with that. So regularization techniques we haven't jumped into yet, but believe me, we'll get there. Let's see. Are these rows for test images chosen at random? Yes, they were. So test images were originally chosen at random. They're not chosen at random dynamically at this point. The test data set, it's not important in general, but in this case, MNIST has a separate test data set already picked out at random. So they're not chosen at runtime, which might be neat, but they're not. That's not the way it is here. They're already separated out for us. Please get a detail of how number of parameters are calculated at each layer. Oh, okay, sure. Let me, since that is simple, let me go back one slide. How the number of parameters are calculated each layer? Well, let's look at the input layer, for example. If we go back to that picture, and it's worth me. Oh man, this laser pointer is going to drive me batty. So if we look at the number of, it's worth going all the way back to a slide like, why not like this one here? If we look at the number of parameters that get us from one layer to the next, so for this layer to this layer, if we look at how many weights there are connecting us right here, there's this many weights times this many weights. These happen to be the same size. Let's go with this. Let's go with this last layer. The number of weights between these two layers is this many times this many. So 4 times, I don't know, 12 here. If you look at all the little weights in here, there'd be, if it's 4 times 12, there'd be 48 lines in here. So our matrix has to be a 4 by 12 matrix to capture all of these weights. So that's the number of parameters. It's fixed by us saying what our network size is. Now on the input side, we have to have 784 because it's how many pixels we have from our MNIST data. And our output side, we have to have 10. And in between, we happen to be choosing 2 layers of 64. So the math from one layer to the next is just simply this number times this number, and that's going to give us a matrix. And so that is what, our model summary right here is giving us. So this is the math. If we look at the input layer where it is, that's 784 times 64, that better be equal to 50,240. So that's the number of parameters in each layer. It's the matrix, by and large, the parameters are those matrix elements plus the biases. There's a bias on each layer too. That's a much smaller number because there's one bias per layer. So there's not so much in the biases, but that's our layers right there. So in the output layer here, like I said, 64 times 10, which is 640, plus our 10 biases. So that's what we have here. So that's what these number of parameters are, and it ends up being the total here. And we're going to see this number grow explosively as we get more sophisticated. Okay, something like AKI information criterion. I don't know what that is, so I can't tell you that. Can RDD data be linked to TensorFlow? Yes, it can. We'll get into that, linking Spark and TensorFlow and how you may or may not want to connect them together. Several options. Number of parameters also include biases. Yes, as I finally got to just now. Yes, it does indeed. Okay, so caught up on questions, and they're all good questions. Keep them coming. So we find our output layer, we want this activation function to be a little bit special. Instead of using ReLU or something else, we want Softmax. Why? Because we'd like our outputs to be a nice, pretty probability values. We'd like our output layer to say, I think this is, let's say we have 3 digits only. So here's a world where we're only training on 3 digits. So let's say we throw something at the network that's the digit, let's say it's the digit 0, so it's actually guessing right. We'd like it to say, I'm 87% sure this is 0, I'm almost positive it's not a 1, and maybe there's a slight chance it's a 2 on 0.1. So we have some nice normalized probability values here, right? This is wonderful and makes sense. However, what we will find coming out of a network, anytime you're looking at it inside a neural net, is the values can range all over the place. From very large, it could go from 1 million to negative 2 million. I mean, the values could theoretically be all over the map. There's nothing constraining them unless we do it actively. And so we'll find typically the output values for this would actually really look like this coming to the output layer. It might look like 4.8, which means it's probably a 0, 2.9, because it's less sure it's a 2, negative 2.6. Well, that's a pretty good sign it's not a 1. So this is what the output actually looks like. So how do we get from here to here? Well, very simple couple of steps. The obvious one to do is if we take and exponentiate these, that does a great job of stretching out the number 1 value from the number 2 and the number 3. And it also does a good job of driving any negative values very close to 0. So we just take an exponential function on these and we get some nice, this is much clearer here to see which one's probably the right answer. And once we've got these, then all we need to do is normalize and basically just take the average and cram it back down so that this is the percentages that come back out. So this is a very simple, straightforward function that has some nice properties on the output side. So that's why we use Softmax at the very last layer to give us some nice looking outputs. On the other hand, we have to come up with an error now. So if we've got outputs that look like these probability guesses here, and we want an error function, what could we do? Well, we could use root mean square here. We could take our squared error difference here. It will work, and you will find, and you can substitute that in for error if you want. It'll train and it'll actually learn things. But turns out that a really effective, good way to deal with an error function when you've got these kind of categorical outputs, and by sparse means only one of them is really the right answer. So we got these kind of outputs here. A good way to do it is cross entropy loss. Name entropy really comes from the fact that we got a logarithmic function. A logarithmic function really comes from the fact mostly that we're trying to undo this exponentiation in some sense. So don't overthink the terminology here unless you are in information theory and you know this is a Shannon entropy kind of thing. But the most important thing to realize is that we're kind of using the softmax because it gives us nice outputs. So our error function kind of with a logarithm undoes that a little bit. And all we want to do is make sure that we give ourselves a big penalty for wrong answers and not so much of a penalty for the right answer. So this is a 1 because it's the right answer and it guessed right, and a 0 for the wrong answers here, and we add them together and we end up with what is cross entropy loss. So this is a pretty effective way to work with data that's nice categories, dogs and cats. So it's simple mathematical definition. It's got a little bit of a hand-waving argument why we use it, and you could certainly do something like squared errors if you wanted to, and it would still work. But this is the loss function that we're choosing. And if we look at our network, we can see how easy it is to plug that in there. We can just say, this is the loss we want. And when TensorFlow, we could define our own losses if we wanted, but we're rarely going to do that because it's got a bunch of losses you'll see in the documentation. And so this is the obvious one to pick for number categories like this, so we'll pick it. And the last parameter here is just saying some metrics that we'd like it to report to us, to collect and report to us. And accuracy is a nice metric to have. It's going to tell us how small our loss is and how good our testing is. So this is what we're going to ask it to tell us every time step. So at this point, we have our entire model defined. This is the full model. It's basic. Well, actually, there's just these last lines of the full model. This is the architecture of the model right here. And this is the solver, the loss that we're going to use, and the solver we're going to use to minimize that loss. So these couple of lines right here completely define our neural net. Now it's time to actually get the thing training. So training here is going to be, we kind of saw model.training in Spark. Well, in TensorFlow, model.fit is going to say, let's train our model. Let's fit our model as best we can. And it has a number of parameters here that are interesting. We have the training images and the training labels. So this says this could be a picture of, this is a list of images of numbers, and these are the appropriate labels, the correct answers to train to. We're going to tell it our batch size, how many to work on at a time, our training batch, our mini batch, and how many epochs or how many times to go through the full list. And so I picked 1, 28, and 40, and we'll be able to print out as we go along how the error is going down and see if this is reasonable numbers. I'm going to ask it to spit out as it's going along some of that information. So verbose equals 1 is a nice thing to have it report some data while it's running for us. And this is a really nice thing that Keras takes care of for us. We can also tell it the validation data to use along the way. So as it's running along, here's what it's going to report as it's running along in training, but it's not going to, and this will give us a really good idea of how it's actually doing as it's fitting the training data. So this is the test data right here. Okay, let's see what happens when we run this particular network. And it runs and it spits out, like I said, we've got it in verbose mode, so it's going to tell us some useful stuff. And it's going to go from 1 epoch to 40 epochs here. I've edited out some of the middle ones here. And one thing it does that's kind of nice is it tells us how long it's taking for each epoch. So it's very quick right here. It actually prints this progress bar in real time as it's running. It's filling out this progress bar. It's kind of nifty. So it's taking 1 second per epoch. So this is pretty quick to train, which is good because it's a tiny little network. It even tells us how long it takes per sample. But more interesting to us is as it's training here are the loss and the accuracy. They're just kind of inversely proportional to each other. So from now on, we'll mostly just look at accuracy. The loss goes down and the accuracy goes up. It's exactly like you'd expect. So if we look at our accuracy, when we're first starting out here, our accuracy is 0.88 on the first epoch as it's learning things. It's not bad for only having one pass through the data. And it gets all the way better up to 0.9999. It's correct. So it's predicting in its training data the answer almost 100% by the time it's done here at 40 epochs. We're going to graph this out. We'll look at it in more detail. But here's the reality. The reality is the validation data over here from our test set, the validation data, which it's not actually using, so it's not fitting to the data, the validation data isn't doing quite so well. The validation data starts out pretty well, but it seems to peak at somewhere around 0.97, about 97% accurate. So this thing is fooling itself in training. It thinks I'm getting it right all the time. It's really good at fitting all of its parameters to the training data. But when we go to the side and look at the data that we haven't trained it on to generalize it and see how well it's generalizing it, we see it's not doing quite so well. It's doing okay. I mean, it's 97% correct, but it's not that well. Okay, let's see. Got a few questions. Are mini batches used inside each epoch? Absolutely. That's the mini batches keep adding up until we get to an epoch. Okay, this is a little bit, again, MATLAB code that'll plot stuff out. I'm not sticking it in the examples. You can just cut and paste this in there if you want. And if you do that, you'll see some nice plots that look like this. So it's a very quick way to spit out some plots of our data. So here's the model loss right here. And we can see the loss goes down as the accuracy goes up. And since the two are kind of roughly equivalent here, we're just going to look at accuracy from now on. That'll be good enough for our purposes. But here's the phenomena of overfitting. We can see what's going on here. We can see that as we're training, the blue here, it gets better and better and better. And we're going to get close to 100% accuracy. It's going to learn these digits really well. But in some sense, and this is, you'll occasionally hear people refer to it as it's really memorizing the digits. Instead of learning what digits look like, it's memorizing them. And that's why it's gotten really good at this. But when we show it new digits, it's not quite so good, right? So it's actually it's peaking here, and we can see we can keep going. We can keep driving this error maybe even lower. No point to it. It's already up to 0.999, but we're not doing any better after the first maybe 5 or 6 epochs. If we go back up here and look at the text data, we're really peaking out here at our 97% after the first 5 or 6 epochs. We can keep going, and we're driving that training error lower. This is overfitting. This is overfitting exactly in the same sense as we were talking about earlier with polynomials, and we can go to higher orders and drive the error to 0. We're overfitting our data, and you can see it graphically here. And indeed, that is how people tell that they're overfitting, is they typically see it graphically just like this. They see, I kept training and I kept driving the accuracy to 100%, but my test data wasn't coming along for the ride. So this is a visual representation of overtraining right here, and we're doing it. So there's no point really in going past 5 epochs, and this network's never going to do better than, as it's set up right now, than about 97%. But, which isn't terrible. It's a good start, right? It's a neural net that can recognize 97% of the characters we show to it. Why sometimes the validation or testing accuracy can be higher than training accuracy. Yeah, early on here, if you look at really early on here, the first bunch of mini batches, it doesn't really capture this until it starts out here early. So by the first couple of mini batches, get this training off to a fast start. By the time it does its first test, the test data has already got the benefit of the early training because it only tests periodically. So yeah, so that's why briefly here, these things can be that the test data looks a little better than the trained data at the very beginning. That's just because, again, it has the benefit of the first epoch of training before it tested it. So don't think anything else into it. It's not really significant or useful. So after you start capturing some data points is when it really becomes meaningful. Okay, so we're doing okay, but we recognize we could probably do better, and we'd like to do better, and maybe we can address that overfitting issue and whatnot. But first, let's see if maybe the key to going better is to go with a bigger network, a wider network. So we had a 64 neuron network. Let's go to a 512 network. Well, with Keras, it's this simple. It's the reason why I've really aggressively moved into Keras here, and why I've become a big fan of it for this kind of stuff. Is this is how easy it is for us to experiment and go to a 512 wide network. We just tell we want 512 neurons right here. Change that hyperparameter. Boom, we're good to go. Rerun the thing again, and here's what happens. We can see that we did actually significantly better here. We're now up to, at the end of our 30 epochs. We won't keep going to 40 because we can see even this thing's peaking early. So why be dumb? Let's just go out to even 30. 30 is even further than we needed to go. But by 30 epochs, we're up to 98.2%. So we've cut down a lot of the error, right? If we realize we had 3% before, we're down to less than 2%. We're doing okay. So we're getting better. We can still see there's absolutely the case where at some point we're just overtraining and there's no point to it, but we can see that we're also doing better. So that was good. Okay, well, here's the model for it, by the way. Let's see how many parameters up to now. The parameters are exploding though as we do this. We're now up to almost 700,000 parameters here, right? Because when you start connecting 512 layers to 512 layers, you got a lot of parameters there. So it's adding up. We're getting there, getting big. But we're getting better results too. And again, under 1 million parameters is still tiny by any normal standard. Okay, how about if we go deeper? Let's go with more layers here. And again, if you'd say, well, can you justify that analytically? How much more accurately we get if we add more layers and go deeper? The answer is no, you can't, and you won't see this in practical, real research. Instead, you have guesses why it might be good, bad, or otherwise to go deeper. So, and mostly you have a lot of experimentation, and after the fact, guessing as to why it worked out that way. So that's exactly what we're going to do. We're going to do the experiment and see what happened. So we do the experiment here with 3 layers now, 3 fat layers that is in our network, and we now have a lot more parameters. We're up to almost 1 million parameters here now. But we're doing a little bit better still. Oh, no, we're not. We're doing worse here. What has happened here? Why are we doing worse with more neurons, more weights? It takes longer to train. We're up, by the way, to now 3 seconds per epoch. So this is actually taking a little bit of time here. By the way, these times are extremely relative. This is on a really, really slow machine. On bridges, this should be much faster. So we're now up to down to 98%. We actually got worse with more parameters. What's going on here? Well, it turns out that we're wandering into one of the problems that we can cope with these days with lots of methods I'm going to show you, but for a long time was thought to be a fundamental limitation of deep learning, which is that as you get deeper layers, the gradients go down. The differences between one layer and the next start to go down as we stretch the problem out. And gradients, as you may recall from looking at back propagation, when I said, okay, even if we don't dive into the math, you can see we're dealing with DWDE or DEDW. We're dealing with these differentials. We're dealing with being able to adjust and push our weights effectively by having some difference to push against. We want to adjust our weights to increase or decrease these differences. If we build very deep networks, the differences become shallow. And this is called vanishing gradients. And vanishing gradients for a long time were thought to be the reason we can't make networks deep enough to be really powerful. And indeed, we're seeing it here creep in already, even with our relatively modest network. As we go deeper, instead of getting smarter and more powerful like we think, we're ending up with the gradients becoming shallower and it's not able to learn as well. And if we actually wanted to prove that, we could, with some tools we'll look at later with TensorBoard, we could actually pull out at runtime while it's running. We can see these gradients on average. You don't want to look at one at a time, obviously, but we can see the gradients get shallower. We can start to see what's going on. And we can tell that that's what we're running into. So this is not a good thing. Let me see. I see some questions just popped up here in my peripheral vision.
4 questions.
Let's see. Note the performance on test data starting better. Yeah, Patrick calculated. Yeah, okay. Let's see. It looks like the loss on the test data is increasing with epoch while accuracy is flat. Is that true? And is that generally true? Yes, that's what overtraining is. At some point, we're not going to get better accuracy. As a matter of fact, very often, if you keep going, it'll get worse. As it overfits even better to the problem, it gets worse. So you will oftentimes see that the test accuracy starts to degenerate because it's overfitting so much. But at any rate, it definitely hits a peak at some point where you're overtraining. Let's see, it looks at the loss. Okay. How do we print out the trained neural net architecture? I'm assuming it's a simple command. It is a simple command. It's the one I've got right here, model.summary. So this is the command. So if you do summary after you've trained your model, after you compiled your model, you don't have to train it. After you've compiled your model, if you do model.summary, it will spit exactly this out. How can I calculate accuracy? Accuracy, it's nice that it does this for us, but it's also because it's a very straightforward thing. And accuracy is just how many of your answers are correct from your test data when you run it back through your trained network. So at some point in time, to get this value, what it's doing is it's saying, okay, here at our 5th epoch here, I am going to stop training, and I'm going to run the test images through our trained network and see how many of them are labeled correctly and how many of them are labeled incorrectly, when it spits out the answer. And that's as hard as accuracy is. It's very straightforward. It's a naive question, possibly visualization in bridges, CLI. You could set up, yes, you could set up matplotlib so it outputs from bridges, but it involves an X window setup. So it's not something we dive into here. It's not difficult, but it's not something for this class. So yes, you can get visualizations out of bridges, and with TensorBoard, it's much easier. And we're going to get on TensorBoard later. With TensorBoard, it's a web server, makes it even easier to do. So I would suggest wait till we get to TensorBoard. It outputs all this kind of stuff and much more, and it'll do it via a web server. Okay. So we find that just making networks bigger and wider and whatnot does not obviously lead us to some improvement, and we can easily run into things like this vanishing gradient here. And so this is about as far as we're going to get with just a simple, dense, fully connected network. And so so there are some terms here you should understand. Our generic networks that we've drawn thus far, one layer connected to the next, are called dense. Every connection between one layer and the next is there. Or fully connected. I think fully connected is probably the term you see most often used in publications because it abbreviates nicely to FC. So you'll see layers described as SC or CNN and whatnot. Fully connected, dense. These are the kind of generic layers that we've used so far. And we found with our problem, at least, we probably hit about the limit of what we can do here without doing something tricky. And instead of trying to get tricky here, let's look at well, before we do move on, let's recap what we've done here. We're going to look at some techniques that are better for images. But to recap, we started out with a little tiny network, very tiny network. It got 97.5% accuracy. We improved that by going to a wider network. And then we actually didn't do much better, did a little bit worse by going to a wide, deep network. So this is where we stand so far. We can do better than this. We're going to do better than this. The way we're going to do better than this is by using convolutional neural nets. This is an extremely important building block of any modern network design. They show up in not only vision problems like this, where it might become obvious once we apply it that, of course, all vision should be convolutional, but it will be in many, many other kind of networks too, like text-based stuff and audio-based stuff. So we'll find ourselves using these all over the place. So next to fully connected, this is the next most important type of layer design that you're going to find. And convolutional neural nets really showed their great power in image recognition and really spelled the end of classical techniques in image recognition compared to deep learning techniques with AlexNet in 2012. There's another standardized data set that's extremely important is ImageNet. And MNIST is simple enough that we're going to crush it before we're done here today. So you need something more challenging. And ImageNet is a collection of higher resolution color images of 100 or 1,000 different objects. So it's a little bit more complicated, including cats and dogs and wheelbarrows and stuff like that. And so it's a more challenging problem. And the competition with ImageNet was hot back in 2012, many different approaches. AlexNet came along, and all of a sudden, the only way to really do vision problems was neural nets with convolution type architectures. And this is what AlexNet looked like. We're going to dive into what these convolutions are here in just this slide. We're going to explicitly jump into them. But AlexNet was a bunch of layers of these convolutional type networks. So we come back to this slide after we go through the next 5 or 6. Every one of these things will make perfect sense to you. But let's first of all look at what convolutions are. Convolution is a very simple mathematical operation too. It's related to, if you remember from calculus, and calculus, when you do a convolution of one function on another, you're basically sliding one function over another, integrating one function over another. And the calculus convolution has its many purposes, but the digital version of that, the discrete version of a convolution, is even maybe a little bit simpler to grasp. It's doing, in some sense, the same function. It's basically, we're sliding these filters over our input image. So this is our input, and this would typically be maybe 1,000 by 1,000 pixel image here. And our filters would actually still be pretty small. They might be 3 by 3, but just to put some scale, more meaningful scale on here. But when we slide our filters over our input image, it's going to give us an output image. As we slide over, it's going to transform our input into an output. And we might slide different filters over our input so that they do different things and get different outputs. But the math for the convolution is very straightforward. All it is we take each element, we paste it on the image here in a location, and we take each element of this and we multiply it by the corresponding input element. So A1 plus times I1. And then we add that to A2 times I2. A3 times I3. So it's very simple. We do that and we end up with a new particular pixel in the output image. We slide the filter over and do it again. Turns out, there's also a little bit of padding. What do I do on the edges? And it's trivial. You can do several different things, and padding it out to 0 is a reasonable thing to do. But you do have to worry about that little detail if you implement it yourself by hand. TensorFlow will do it for us. We won't worry about it. Its defaults for handling this stuff will be sufficient for our purposes. But I hope you can appreciate the math is very simple. So there's nothing hidden behind convolutions that are tricky. But what isn't so obvious is how amazingly powerful these convolutions can be. So here's a convolution called an edge detector, that if we pass it over this image here, ends up resulting in this image. And that does do, to me at least, an amazingly good job of somehow highlighting edges. A very simple mathematical operation, and yet we pick out a lot of edges in this image. And so these can be fantastically clever and powerful for how simple they are. And indeed, for a long time, the convolution, or a digital convolution, referred to one of these nice hand-constructed convolutions that were used in cameras and in early machine learning and everything as a way to do nifty things to images, to blur images or whatever. There's lots of different edge detectors you can build by hand to do nifty things. But what we're going to find in machine learning is that our convolutions are not handmade by us to do specific things. Instead, we're going to learn convolutions. The system, as it's training, is going to learn convolutions that can do the right things for what its task it's trying to learn. If we show it lots of pictures of cats and dogs, it's going to learn convolutions that can do, maybe pick out some edges on the images to begin to see things, and then some other convolutions will put those edges together and picture eyes and ears. Some other convolutions will get good at putting together all those shapes and saying, this is a cat, this is a dog. So the convolutions will learn different things, but they're going to change as the model runs and trains, not like our handmade one that we've got here. So this is the way our convolutional network is going to look. As we give it a bunch of input pixels in an image, the convolutions will scan over that image and figure out things and transform things into our new image that's transformed. And then at the end of almost any network like this, we're going to have a fully connected, that's what F here, fully connected layer that's going to actually put all the pieces together. So fully connected layers are really smart because they've got all these weights in them and they're very flexible. Whereas convolutional layers are really good at scanning over a whole image. They don't have to have enough weights for every pixel. Instead, they can scan over the image and do things. The combination of the two is what makes them effective. The convolutions will find things and then find higher level things in the image. They'll pick out the edges and then eventually the ears and the noses. And they assemble all that information at the highest level. Will typically have a fully connected layer or two because they're so smart, they can put all the puzzle pieces together now and recognize dog or cat. So this is a typical flow, is a convolution and then fully connected layer. Well, more typical is actually to have multiple convolutions. We really stack these convolutions. Like I say, the early ones will find simple low-level details like edges, whereas the higher level ones will start to put those together. And the highest level ones still, as we have many more layers, will figure things out. And eventually you have convolutions which figure out that's an arm or that's a leg, and then put those together. That's a dog, that's a cat, that's a cow. So the layers will go from low-level content up to the context of the image. So, and we'll see this represented in various forms as style and content and whatnot. We'll get there. Let me see if I should take a pause.
Yeah, 4 comments.
I'm with you, Steve. Let's see. Test accuracy, validation, non-example. Yeah, the accuracy is when we're running this, it's printing out both. It's printing out the accuracy of the of the training data and the accuracy of the test data. This is a little bit confusing here. I'm sorry that this is the way TensorFlow chooses to label it. It's using the test data and calling it the validation data, which is kind of correct in a sense in that it's really being used in this process. So it's not on the other side of a wall. So somebody could use it to adjust. So anyway, in this case here, the test data is being compared to what's coming out of the MNIST test data set is being used to print out the validation data result. So, and the training data is the training data. So it's a little bit of a mix of those terms there. Let's see, in general, should the GPU nodes allocations we get with have network access? No, in general, so this is one of the reasons why it takes a little bit of effort to set up graphics from the GPU nodes, is that the GPU nodes are in general and the compute nodes, the nodes on bridges are not allowed willy-nilly access to the outside world by default. You can turn that on with egress and stuff. I just don't want to distract everybody with bridges specific stuff right now. We're not here to teach you how to use bridges right now. I'll be glad to teach you how to use bridges after the workshop, but the detail of getting bridges node to connect to the outside world is it's not difficult. It's a flag called egress, and you just point things in the right place. But that's what's needed to get graphic access. Oh, somebody actually, Tom actually jumped into that, so he answered the question already for me. So yeah, I'd suggest that don't get too distracted in the middle of my lecture though with trying to get that to work, because it's not a big deal, but it's also not useful. I mean, it's not interesting details. Okay. So here's a picture of a convolution in a real application. Here's what it looks like a little bit more as we scan a convolution over an image. And we might have, coming from the previous layer, 3 different types of things. We had, maybe the previous layer had 3 different filters spitting out different things. One of them was detecting vertical edges. This one was detecting circles. This one was detecting high contrast. So we can have different filters doing different things feeding into our layer. Or maybe even it's the first layer, and sometimes you can have one of them be R, G, and B. We can have 3 different channels for color if it's color image. But at any rate, we've got 3 things coming in from the previous layer. And we decided, as a hyperparameter, we're the designers of the network, and we decided it might be nice to have 2 filters, 2 different things output on the next layer. And again, these are hyperparameters we have to choose. The problem is not going to pick them for us. We have to use experience, intuition, existing problems, and experimentation. So we decided in this particular case, for whatever reasons, we've got 3 layers coming in from the 3 filters coming from the previous layer. We want 2 going out in the output volume. And here's the math that it's going to do. So it starts out and we're scanning, each filter scanning its own region of one of the input coming images. And it's doing its math. And then it's adding them all together, and it's ending up with this output value here. Since this is the 1 layer instead of 0 layer, here we go. Here's the output value. It's basically just doing all those dot products, all those add multiplies. If you do step through them all right here, all of these 27 operations, you'll find yourself here with a number 4. Okay, then we move the filter over. We stride it over. How much we move, it's up to us too. We could move it 1 pixel, we could move it 2, we could even move it 3 at a time and still cover the whole image. So your stride of your filter is an option you have too, another hyperparameter. So we move the convolution over in this case, and we have more of the same math to figure out this pixel right here. We do the same thing again, and we scan the image like this, and we end up generating this output volume right here that we can pass on to the next layer. The next layer will expect 2 volumes coming into it, and it could output 3, and it could output 10, or it could output 1. So it's up to us to decide how many filters we have coming in. By the way, filters and kernels, these are again kind of interchangeable terms here. So you'll see them, hear them called different things. So we can decide how many filters or kernels or convolutional filters we want coming into and going out of the image. But that's the mathematics of how it plays out right there. So I hope everybody's comfortable with this idea. The convolution scan the image and input volumes and output volumes happen. Here's actually the mathematics of it if you care about it. How many weights we've got involved here is each convolutional layer has an input volume that's the width times the height, so that's the resolution of the image, times the depth. How many channels do we have coming in? Again, it could even be RGB from the first layer, but it can also be a bunch of features on an intermediate layer. That means we have a bunch of hyperparameters here with the number of filters that we want to apply. We have the size of the filters. They can be 3 by 3, 5 by 5. AlexNet was 11 by 11 on some and 5 by 5 on others. We have the stride, how much we want them to jump. And padding's boring. It's just on the edges how we want to pad things. That's not real significant. And we have, as a result, an output volume that has, if we do the math here, what we got, all the parameters, we got an output volume that's going to be this size. So this is the math of how many parameters we have. And it's not exciting. I hope it makes intuitive sense to you, but it shows you how the parameters add up as we have more filters and whatnot. And so we end up with a bunch of layers. Now, it so happens that, as I've mentioned, one of the things that convolutions do is they learn lower level features and higher level features. So it so happens that we might like to zoom out on the image as we're looking at it. We might like to have the first filters go through the image and find all of the edges. But as we start to assemble the edges into things like ears and noses, we might want to kind of step back and look at the picture from a higher level perspective. And you could actually do that by having a convolution just kind of shrink the image down. But it turns out that a very effective and direct way is let's just zoom out on the image ourselves by using a pooling function, a zoom out function essentially. And pooling says, let's collect some pixels together. And it's exactly what you do in Photoshop if you take and shrink an image down. So if you're in Photoshop and you have a 1,000 by 1,000 image and you decide to fit it on your web page and have it load faster, you'd like it to be a 100 by 100 image, you can take and shrink everything down by a factor of 10 just by taking each little 10 by 10 patch. And you'd probably in Photoshop maybe average the pixels. Photoshop has a number of options for it. It can get fancy, it can get stupid. Can smooth things out, but the simplest way might be just to average the pixels. And indeed, that's a technique that's available to you in neural nets. The most popular pooling method, though, is one where you just take the maximum value of those pixels. In this case, it looks like this pooling layer here is taking 4 pixels at a time. And what you would pass along is just the maximum value of one of those pixels. And that would shrink our picture down by a factor of 2 in each direction. And maximum is nice. Wouldn't be so nice in image processing, maybe. It would make things a little maybe sparkly. But image, it's nice here because a lot of times the convolution that's lighting up the most means it's really detecting a feature that's most important, like maybe an edge or something. So you maybe want to highlight it. Again, a slight hand-waving argument. And max isn't always the best, but max is the most common. It's the one we're going to use here. And it's a way of zooming out on the image. So this way we can go to our next convolutional layer and have it be a smaller layer and have a bigger level perspective on it. Maybe now we can take advantage of more kernels because we're, got fewer convolutions. We can have more features. But at any rate, it's a way to zoom out on the image. So pooling and convolutional layers very often go together. And indeed, if we go back, look back at AlexNet here, here's a different perspective on it. We can see it's nothing more. As complex as it looks, it's a bunch of these convolutional things here. They're 11 by 11 convolutions, if you squint here and look, that scan over the image to begin with. And then it pools down, it does max pooling here, and it shrinks down more. And we have different numbers of filters at different levels. And eventually ends up in some dense layers at the end to kind of assemble all this information. So this is what it looks like. Now, if we look at what the filters are learning here in AlexNet, I keep saying they're things like ears, noses, or edges, but in reality, these convolutions as they go along do not learn things that are that human interpretable. Again, it shouldn't surprise you because that's been a theme as we've looked at machine learning algorithms so far. I keep saying the latent spaces in our recommender system, for example, are not as simple as actor and director and genre. They work, they are latent effect, but they're not something that's human interpretable. That's even more so true in deep learning. It's very frustrating to people, and we try very hard, and we've had some success at beginning to tease meaning out of these things or inject meaning into these things by design. But by default, these convolutions are very abstract. They work. Somehow AlexNet's incredibly good at recognizing lots of different images, but here's what each one of these convolutions look like. These are the 96 in the first layer. They're stacked because it is learning RGB channels in that first layer, they're color images. And I can't tell you that this filter finds edges. It doesn't. It does something that in conjunction with a bunch of other filters does something else useful. And ultimately, it's good at teasing out the information out of these images, but they're not explicit. Now, we can tell in various ways that as they go from low level to higher level, they go from doing things like finding edges to eventually assembling high level content. We are good enough at researching and understanding these things to understand that, but you can't pull out one of these and say, this finds ears. Okay, let's make one of these things. Questions here? Let's see. Local contrast norm layer in AlexNet. That is a normalization function to try to, as I said, we like to keep things, especially with images, things from getting too bright or dark or whatever. So you want to normalize things. We'll talk a lot more about normalization. We'll actually look at the current modern version of it, which is batch normalization, in a little bit, just a couple more slides. So this is a more primitive version of layer normalization, not batch normalization, layer normalization. So this is a more primitive version of it. We'll get into that. Okay, So let's build ourselves a small network here, convolutional network. And once again, Keras is incredibly powerful and friendly and high level. It's very easy to do. All we need to do is substitute for our dense layers that we had before is a couple of convolutional layers. And we need to correct our geometry a little bit because now we're doing the thing that seems so sensible, which is keeping the shape of our images. Our 28 by 28 characters now are going to go through this system, maintaining, at least till we get to the last flat layers, they're going to look like 28 by 28 characters. Our convolutions scan over these 2D images. They take advantage of that locality of information, a geometrical relationship between pixels. We're going to benefit from that and keep that. It seems sensible to do. Why did we throw that out before? Well, we have to if all we have are dense layers. Convolutions allow us to keep that structure. So now, instead of stretching these out to 768 vectors, we're going to keep them as 28 by 28 pixel images. So we're going to keep these. And now we've got our convolutional layers here. Actually, we only have one convolutional layer here with pooling. So our first convolutional layer here is going to have 32 features to it, or filters. This is up to us to pick. So we pick 32. They're 3 by 3. Again, it's up to us to pick. And the input shape is not up to us to pick. It better be 28 by 28 coming into it. So these are some hyperparameters that we pick. 32, 3 by 3. Our pooling is also something we pick, and we're going to pull down by a factor of 2 by 2. So we're going to introduce one convolutional layer here. Then when we're done, before we go from our convolutional layers, which are working with these 2D images, we do need to flatten things out before we feed them into our dense or fully connected layers. We're going to pick our final smart layer is going to have 100 neurons in it. And again, that's a hyperparameter we pick. And so we better flatten things out to feed into those 100 neurons. And ultimately, we better have 10 neurons on our output layer again, because we're doing 10 digits. We compile this thing. This time, just for the heck of it, hey, why not use stochastic gradient descent here instead of atom? So we're going to use stochastic gradient descent with some momentum and some learning rate that we pick ourselves. It's not an adaptive learning rate here, like it's not as smart as atom, but we're going to try this out. Why not mix it up? You can see how easy it is to swap in a new optimizer. We just pick a new one. Okay, so otherwise we've got something that's, takes us a couple of minutes to edit in compared to our, evolving from our completely flat model, our dense model, fully connected layers. It takes us a couple minutes. We've edited this and boom, we're now into the world of computational modeling, convolutional networks. Let's go ahead and do it. If we do it, here's what we find for our output. We are doing better. We find out after 10 epochs here, we're not going past 10 because again, we can see this kind of plateauing. So why waste our time, especially because it's taking longer to run now. With the number of weights we have in a more complex operations, we're up to about 12 seconds per epoch here. Again, this is an arbitrary scale. This happens to be on the same machine I ran the earlier tests on. Very slow. Now we're up to 98.7% accuracy. Okay, we're making some real progress here with a network, by the way, that's not that much more complex weight-wise. We only have 500,000 parameters here. It's actually smaller than our 3-layer network we had previously. So we're doing well here. We have not that many parameters. It's still a fairly small network. It's a very primitive network in some sense. And our accuracy is better. We're still got some room here to improve. We're overfitting at some point, but we definitely did improve though. So to recap, we're heading in the right direction. Well, let's keep going in this direction here. Let's scale up our CNN. Let's go to multiple layers because why not? Seems like that's a thing people do that ends up being very effective. And so all we need to do here is add in one more convolutional layer right here. Boom, here we go. Let's add another convolutional layer in. In this case, we actually have choices here. We could add it in after the pooling. We could add in a convolutional layer and pooling. So we're it's not just saying we're going to another layer. We still have options. As a matter of fact, we have exercised a little bit of creativity here. We've gone to 64 features in this next layer. So here we go to 64 features instead of 32 that we had before. We're going to go to 64 features in this layer. And that's pretty much what we've stuck in here. And let's run this and see what happens. And we are doing better still. We are now up over 99%. And we're getting there pretty quickly too. Up inside of about, I guess, 4 epochs or so. If we go back and look at this, we're already up there. We've got more parameters now, definitely, with this bigger convolutional layer with 64 features to it. So it's got a lot of parameters in it. But we're getting to be better at this. And so we're heading in the right direction. Now, this overfitting region that is our cumulative score thus far, in case you're losing track. So we are heading in the right direction. This overfitting problem now, though, is something that I think it's time to address directly. So we could keep trying new different architectures and designs and everything, but it's very clear that the overfitting is is catching up with us early on in this, and it's just we're not benefiting from any of this training later on. So what's a regularization method that works with this type of scheme? Well, it turns out one that was introduced back with AlexNet, in that era at least, is a crazy idea called dropout, which is that let's just rip out some of our neurons in our fully connected layer. Let's just intentionally brain damage our network while it's training. And so that's why I've got our mind blown emoji here, because we're doing it in two senses. First of all, it should kind of be a mind blower that it's helpful to just rip out neurons randomly in your network while it's training. And in a sense, we're blowing its mind too. I mean, that's what we're doing. And this is going to be very effective. So the notion's kind of crazy. It's an example of how deep learning has crazy notions people throw at the wall and they turn out to be useful. It also is incredibly frustrating to analyze analytically. This is the kind of stuff that drives the theoreticians crazy, because stuff's already nonlinear enough without us turning on and off chunks of the network while it's training. But again, we can come up with some hand-waving reasons why it works, kind of. Some people view it as an ensemble method. In other words, we're training multiple different networks simultaneously because we're making and breaking connections. So you got multiple networks. And if you train multiple networks to work on things, at the end they're useful because they can kind of vote on the correct answer. If we train 10 different networks to recognize digits, we might expect that if we take a majority vote of those networks, that might be better than any one of them. And that's kind of what we're doing in a way. That's at least one way you can view it. Another way you can view it, and I like Schmidhuber's view of it, he's a pioneer in this field who's done a lot of innovative things, been around for a long time. It can also be viewed as a form of training set augmentation, something we haven't come to yet, but basically saying that we're looking at the data differently, the same data set differently. We'll come to that later on. But at any rate, this dropout technique, which again really does defy any in-depth, precise analysis, turns out to be very effective. Let's see how hard it is to implement in Keras. Turns out to be trivial. We can stick in dropout layers anywhere we want. Well, pretty much we want to stick them before dense layers. So we stick in a couple of dropout layers here. The parameter to drop out is how many we want to drop out. And it turns out to be what I think is an astonishingly high number quite often. We're going to drop out a quarter of the neurons here and half of them here. And they're random. It changes from one iteration to the next. So we're going to randomly pull these out. You want to make sure you change up which ones they are, and that will be taken care of automatically. It's also a little scaling and stuff you want to do. It's nice that these layers take care of all those details themselves. But at any rate, we can plop in some dropout here as simply as this, add them into our network and see if this helps us at all. And boop, here we go. We've got a much better handle on that overfitting issue. We've made a lot of it disappear with this crazy dropout technique. Wasn't expensive at all in terms of parameters because the dropout layers really don't have any parameters. They're not training to do anything. Wasn't particularly expensive in terms of time because one can imagine it's not that expensive to zero some things out. But our accuracy went up a good bit. We're now up to 99.2%. That's near the threshold of what's considered superhuman accuracy or human level accuracy on this problem. And we did it with, again, a crazy technique that took us very little time to implement. So I'd say at this point, we're getting pretty much near as good as we're going to get for a simple problem. We're better than 99% accuracy. Squeezing out that last 0.8% is going to be hard because some of the digits are ambiguous even for humans or mislabeled or whatever. So we're getting near human accuracy. We're going to call it quits on MNIST here, and we're going to definitely declare victory here because we've done a fantastic job with a relatively small network that runs very fast and is a very, very small and easy to specify in Keras. So let me take a pause here and see what kind of questions we have here. Train multiple models conventionally without dropout and use them in a multi-model ensemble. They generally outperform a single model. Ensembles almost always outperform unless there's something broken a single model because in some sense your training goes up 10. If we got 10 of something in an ensemble, I've spent the effort to train 10 things, 10 times more computation. I better hope that they're better, that they're better. So ensembles always, should always, unless you're on the, you're heading down the wrong path, be effective, but they're expensive. And that's why they're not typically used much anymore. I'll come back to that in a little bit. So ensembles have really dropped out of favor because they're expensive. But if your ensemble doesn't do better than a single model, something is probably wrong. I mean, that's true that's the wisdom of the crowds with people too, right? So in some sense. Okay. Are the neurons with lowest weight dropped? No, it is absolutely random. It is 100% random. You don't want to drop the ones with lowest weight. It is an interesting idea that we find out that nature shows us that neurons do prune. Low weight neurons end up getting pruned out to 0. And maybe there's something to be learned there. And so modern, both network designs and software and also in hardware do like the idea of absolutely at the end of the day, just pruning, don't have low weight connections. But that's not what's, we're not dipping into that level just yet here. Instead, we're just picking random ones. When you drop out layers, you can add it again, the second drop, etc. You're not dropping out a whole layer. We're only dropping out some particular connections in layers. And for the second dropout, and they're random, so some of them could repeat. When we've got 50% probability, a good many of them are going to be repeated. What accuracy value is acceptable? That's a good question. That's up to you. As I said, we're calling it quits here because we're coming up on human level accuracy. That's very often that's a threshold that people seem to like in machine learning, is when you hit human accuracy, whether it's chess or in this case MNIST. And human accuracy in MNIST, I think people say, is something around 99.2 or 3. That's the level at which people do start to mischaracterize characters themselves or whatever. So that's a pretty good goal for people. And with AlexNet, or excuse me, with ImageNet, which AlexNet trained on, with ImageNet, for example, about 2017, it went superhuman accuracy there, and then people kind of lost interest in it as a research problem, although not as a benchmark. ImageNet still used a lot as a benchmark for hardware and whatnot. Even on the very largest, latest supercomputers. Fastest machines in the world still use ImageNet. They try to solve ImageNet to human accuracy in like 8 seconds, is the Japanese machine that's being stood up right now. But at any rate, human accuracy is a benchmark that you can use if you want, but you could strive for better than that. But in our case, we're going to quit somewhere close to human accuracy. Let's see. One test accuracy, training accuracy, low. I addressed this before. If you keep staring at these, it's basically because at the very beginning, it's just a matter of when you start testing. The training starts getting tested at, the first batch level gets added up. We don't go and take it aside to go test until we've actually already done some training. So it benefits. It's basically starting a little bit later in the testing game. Just an artifact of the way we start testing. If we started testing after 0 training, they would also start out very low. So there's nothing interesting happening when there's a crossover on some of these at very low levels. So don't pay too much attention to that first fraction of an epoch. How to decide what to drop? Is backprop a factor? No, the dropping is just completely random, stochastic. Pick half the connections or a quarter or whatever we specify and drop them. How do we implement early stopping in Keras? Oh, absolutely. So early stopping, we'll get onto that with TensorBoard and whatnot. There's a variety of techniques and strategies you can use, because early stopping, if you recognize you're wasting your time with overtraining, more with this case down here than with this case here, we're finally getting into this overtraining regime right here at the end. So running past here, it's going to get bad. If you can recognize overtraining happening, it is good to stop. Why waste your time, right? Although it's not that trivial. It might seem obvious because our earlier cases had this huge gap. How about here? When are we overtraining? The second that one flips past the other, well, we might stop too early. We're still benefiting here. So it's not trivial, but at some point it does become obvious. So you do want to be able to early stop. And there's a variety of ways you could do it. I mean, we could stick logic in our code right here. This is, in some sense, Python code. We could stick in logic and say, if our accuracy is this much greater than our training accuracy, test accuracy is this much greater, or whatever, you could say stop, halt. But that's not the way we'll actually do it, because that gets a little more complicated. And we'll come back to how you can do that with in the real world with help from, say, TensorFlow, with some direct programming, with frameworks like scikit-learn or Spark that are built around it. Because when you're testing lots of hyperparameters, you don't want to waste your time once you find out your hyperparameters aren't great and you're overtraining silly. Yeah, who wants to waste a lot of time continuing to train? So we will look at stopping early. Possibly to copy your slides or review more detail later. Yeah, the slides are online. Let's see, clarify number of parameters calculation for convolutional layers. Yes, for convolutional layers, the number of parameters are explicitly explained on, this. It's basically the size of your kernels times the number of kernels, or how many parameters you have. So, I mean, here's the volumes that are coming in and out, which takes up the memory, but basically how many filters do we have and what's their extent? That's how many parameters we're trying to train for the filters. So if we have 64, filters, 3x, that's how many parameters we're trying to train and learn. That's why convolutions are so efficient, because they don't, instead of trying to learn parameters for all the pixels, they're only trying to learn enough parameters to make their one little window work really well if they're sliding over everything. So they're only trying to learn their window of pixels really well. Now we want to have lots of different filters and everything, so we start having lots of windows, and they generate lots of training volumes. But the idea is that we have a lot fewer weights. That's why we can see our convolutional networks are not exploding in parameters. Here they're quite modest. Most of the parameters here are in our dense layer, right? Look at this convolutional filter, which worked pretty well, right? Only had 320 convolutional parameters, right? That's extremely efficient. So that's one of the benefits of convolutions, is we don't have many parameters. But absolutely, take a look at these and make sure that you do kind of get at least to within a couple percent what these parameters are, where they come from. And we can see that we don't, here even with 24 by 64 features here, we've got, not that many parameters. Okay. And there are biases too on convolution layers typically. So if you want to do the exact math, you should count on some biases in there.
I think there's 2 new comments.
Okay, let's see. Let's see. Slides are here. How do you implement TensorFlow on Spark? We'll see. There's a way to mix and match them, and we'll come back to that topic. I'll talk about it in more detail when we're done talking about TensorFlow. Trying to develop DNN for inverse. Do you know of any GitHub repository, super resolution, compressed sense? We'll get to very application. I welcome your questions about very application specific stuff, but let's hold off on those to the end because they're not of general interest, but there are probably other people that are specifically also would like to hear your answer. We'll queue those up, the very application specific ones again. So I love the application specific stuff. It tells me you guys are ready to go off and use this stuff, but let's defer those to the Q&A at the end if we can. So don't let me forget that though, as it scrolls up off the screen. I want to come back to that question. Can we speak DNN versus boosted trees? Well, since we haven't talked about boosted trees a lot, so I don't want to confuse people who don't know anything about them. Boosted trees are a very classical machine learning technique that, again, and they're very effective. They are still remain an effective technique, one of the most effective techniques, but they are being obsoleted in most areas where they were effective by deep learning techniques. Absolutely being beat everywhere that they used to be the best in class. That's my general comment on it. We can go into specifics otherwise. Occasionally they're used complementary. You can use boosted trees as inputs into neural nets. But again, without me explaining what boosted trees are to everybody, I hesitate to spend too much time on that. Okay, there's another layer between layers that's kind of in a sense like dropout, that's also very effective. This technique it really addresses the vanishing gradient problem that we saw earlier, even with our simple little 3-layer network, and which you definitely see with, people like to build the networks now that are hundreds of layers deep because there's a lot of power to be had in there for having a lot of convolutions do things. Vanishing gradients are really a difficult problem there. So how can we solve that? Also, sometimes you have exploding gradients in situations that are bad. So how can we deal with that problem? Well, one technique that has become extremely popular is batch normalization. And batch normalization says that what we'd like to do is have the outputs from one layer to the next be normalized, be in some regime. Instead of going very large or very small, which happens in vanishing gradients, what if we resample them after we're done, before we feed them the next layer? What if we resample them and scale them all up or down, or change the deviations in the right region so the next layer has some nice values coming in? And by nice values, I mean it's nice, first of all, if the values stay somewhere around where the activation function's interesting. So with ReLU, for example, it's nice if we stay somewhere around 0, so the activation function's doing something interesting instead of it being a bunch of large numbers that there's no activation function to speak of, it's just a linear function. So keeping things normalized is, again, I hope it appeals to you intuitively, even as a human being. If I'm looking at a bunch of pictures, I don't want some to be murky and some to be very bright. Well, again, layer to layer, that applies as well. And so batch normalization is an idea of taking and doing, after you do reading a batch of results, look at how the weights have spread the input and outputs around, and let's normalize them back so the next layer has some normalized inputs. And we can put those at any layer that we want in the network, and Keras makes it trivial to do that here. Now, there's a little bit of issue. People see this as a kind of a replacement in some sense for dropout in some applications. And you can look at it, even though they don't do exactly the same thing. You can look at it as it's not compatible with dropout. And you can make arguments. And this is what, once again, where we go, the theoreticians are in a conundrum because they like to think about dropout and batch normalization as doing certain things, certain distributions on your data. And so you can argue that they're incompatible. But on the other hand, sometimes they do work together. So there's debate and research going on in this. Maybe the latest paper I saw that I thought was pretty good on it, they did a pretty good job of discussing all these things and find out one general way to maybe look at this is in general, not always, but if you do dropout after all the batch normalization layers, that seems to be a way to mix and match them that's compatible. They make some theoretical arguments and certainly some compelling empirical arguments for it. Do you do it before or after the linear activation function? That's something you'll see talked about. And so, okay, we know there's this linear activation function, but so far that's all been hidden in our layers. We've been using Keras in its highest level version where a convolutional layer does everything for us. It does the convolution, and then it does the nonlinear activation function on it. It does everything for us. It does the bias for us. We've been doing our dense layers. We don't worry about the matrix multiply and then doing the nonlinear activation function. We've been treating it all as just a layer and letting it take care of it because that's a wonderful and convenient and very often exactly what we want to do. However, sometimes you do want to peel into the layers a little bit. Like, for example, there are people that think that batch normalization should be done before the activation function. Some people think no, after is fine, but Keras makes it possible for us without great pain to dig into that level if we want. So if we wanted to peel our layers apart, we could do a little more micromanagement like this. Here's where we're adding in a convolutional layer, but we're actually not specifying the activation function so that we can put it afterwards. So this does the batch normalization before the activation function. Here's where we're not specifying the activation function. We're specifying it explicitly down here. We're going to use a different activation function, a leaky one, which means it leaks a little bit on 0. So it does pass through with this coefficient. Then we're going to do the batch normalization here with some momentum. So we can get into micromanagement if we want with Keras. TensorFlow 1 tended to make that mandatory a lot more. Actually, it was nice in teaching people because it could expose all the guts the whole time. And I could say, hey, you can see matrix multiply here. It's not that complicated. With this approach, we're hiding as much as we want, which turned out to be an awful lot of it. And that's what people generally do. But we can peel things down if we want. And batch normalization gets into that discussion. Should it be before or after the activation function? Again, it's open to debate. And you can make theoretical arguments in both directions. And empirical evidence also leads in both directions. Okay, let's try it here. Why not? Because it's easy to do. Let's throw some batch normalization layers in. Hell, why not throw in 3 of them here? Let's throw them in everywhere that we can and see what happens here. And if we do that, we find out it definitely has a very dramatic effect on convergence here, how quickly things train up. So it seems to have a good effect. But on the other hand, it definitely also, because of that, peaks really early. Is it a great peak? If it's a peak at 99.5 or something, that's a huge win. Trains fast and is accurate. Well, trains fast, turns out it's not quite so accurate. Peaks out at 99.91. That's not terrible, but that's not as good as our last approach. This actually adds some non-trainable parameters here. The non-trainable ones are the batch normalization ones. That's some statistic stuff. Non-trainable here specifically means things that backpropagation doesn't tweak. Backpropagation doesn't directly tweak the parameters that batch normalization uses. So it does have some parameters to keep track of these standard deviations and means, but they don't get adjusted by backpropagation. So not many parameters. It's not expensive in that sense. It does add some time on, though. It looks like it takes a lot of time to do that analysis. So it is expensive time-wise, not parameters-wise. But most importantly, it doesn't seem to be working, just throwing it in right here for us. And that makes sense because our network wasn't, to go back a slide here, our network wasn't particularly deep. There's no reason to believe that we had any vanishing gradients here. So, you know, to an extreme degree, they were starting to vanish some, but because as we went to 3, but it wasn't probably the #1 handicap. So, so it didn't do anything for us, but it was also a painless experiment. Very easy to try to spit out these results. And as I said, as you're doing these yourself, I will encourage you to insert into this code that little clip that I had from Matplotlib. To just stick them in here and print out the results. Or to use TensorBoard, which I'm going to come to next, which will capture and do a lot of stuff for you. But there's no reason to be flying blind. Although you could also, if you're good at just eyeballing data, you could also just look at this and figure it out too, I guess. It's the same data in some sense. Okay, so here's our score with batch normalization. Turns out it's not really a big winner for us. So in the way we've applied it right here, maybe we're not applying it right. Maybe we should have less of it. Maybe in a different, so maybe we should apply it after an activation function. Hey, welcome to the world of deep learning where there's more open questions than there are time for you to explore. But I hope you can see that Keras makes it very easy for us to explore these things. So that leads us into, as time is becoming a question here, that leads us into what is an incredibly beautiful demo that I hope to pull off here. And I don't do many real-time demos or real-time coding in any of my talks because I hate to fumble around and waste people's time. But here's one that's irresistible to me because it illustrates exactly what we've been doing here. It's a network very close to what we've been doing. We could turn ours into this network with very little effort. So here's a network that is in real time going to show us how this stuff works. When I first found this, it was a gentleman from Canada. That's why the website's up here with this. He's since now moved right across campus to us here at Carnegie Mellon. And here's his demo. And let me pull up in real time. Let me fire it up here if I can. Bear with me because I should have pulled it up beforehand, but it's worth doing in real time, so I'm going to. So this is a demo. Here's a picture of what it looks like. That's what I need to do. I need to turn off my laser pointer so that I can click on this link and get something to happen. And here we go. Okay, so here is something that's running in a browser in JavaScript. So that's an important point to keep in mind. It's some terribly pathetic browser on my laptop at the moment, as a matter of fact. And yet, here if we draw a digit, let me draw the digit, say what I think is a passable 2. Boom, in a matter of a fraction of a second, you can see it recognized the digit 2. You can see its first guess here is 2. The second guess doesn't matter much. So that's impressive. But more impressively is here we can visualize exactly how we got 2 out of the input data. So here's the input data here. I don't know if you can see my cursor here. Let me switch it back to laser pointer. I think this is frustrating. So I don't think you can see my cursor, and I need that to be the case. So let me go back to laser pointer. Bear with me. I think if I do a alt tab, okay, I do believe I've brought this image back. Web browser back. Okay. Well, you may, you don't need to see my cursor. You can see its effect right here. So if we look at this right here, I am now, this input image here draws upon, or the input image is drawn upon by these convolutions in the first layer. If we look at the architecture, it's got convolutional layer, downsampling layer, convolution layer, downsampling layer, and a couple fully connected layers. Here's the first convolution layer. If you hover over any of the pixels, you can see where the convolution grabbed those pieces from. So this is very nice. You can see exactly where it's drawing from. Now, one thing that you can immediately observe is that what the convolutions are doing here in the second layer is not entirely obvious. These convolutions have learned to do something that kind of looks like it's actually picking out edges. It's reasonably, I'll guess it's picking out some vertical edges here, maybe horizontal edges kind of sort of here, but it's not that simple. But it is picking out at least kind of edges. That's common enough. The convolutions in the lowest level layer learn to do some kind of things like that. But we can see exactly where it's drawing from. Then we have a downsampling layer here, nothing too dramatic. You can see where it's drawing from, but it's not really doing anything interesting. Then we have another convolutional layer here, and you can see exactly where it's drawing its pixels from. Now, what these convolutions are doing, I have no clue. It's impenetrable. They really, you're gonna have a hard time guessing what features they're pulling out here, but we've got a bunch of features that are being pulled out. Then there's another downsampling layer, and then we move on to the fully connected layer. The fully connected layer draws from all of these image regions right here. And we can see all these pixels drawing from all these regions before they feed into the last fully connected layer. So these last 2 layers are fully connected and are trying to assemble all the pieces the convolutions have given it to the point where we can finally see where the value 2, which is the most lit up one here on the final output layer, comes from. So you can see here, you can explore what's going on. You can see the convolutions do these abstract things. And you can see that this happens in real time. Let me draw another character here. Let me draw a 3, and you can see that this thing, even though it's running in a web browser in JavaScript, is almost instantaneous, which illustrates another point, which is that training can take a long time. This thing may have taken a good bit of time to train, but inference or the forward direction. And that's a term for the forward direction, is inference. When you're actually using the thing in the real world for production, whether it's driving a car, recognizing digits, analyzing text. When you're done training and you turn it over to the real world application, that forward direction inference is very, very fast because all it's doing is a bunch of matrix multiplies. Finding the weights for the network takes a lot of effort with back propagation cycles and everything we've been doing. Once we're done, the inference part is so fast that my web browser running this in JavaScript here can do this instantaneously, basically, and pretty accurately too. It's pretty good at guessing these digits. So that's as far as I'm going to go with this demo, but I encourage you to play with this demo, as much as you'd like, as much as you want to learn from it, because there is a lot of intuition to be plumbed from it. Okay.
John, there's one question, 4 comments back from Sultan.
Okay, let me see. Okay, what is the argument? The batch normalization after rectilinear, important to normalize. One should batch normalize, then ReLU. Well, yeah, so you can get into this. You can get into the discussion. If you're interested in this as to what order to use it in and why, then there's a reason I cited this paper right here. If you're at all, and it's not that difficult of a paper either. If you're at all interested in this idea of when it should be applied, because you can make arguments that make perfect sense and then reality shows it's a little bit different. So if you're interested in where you should apply dropout layers instead of just empirically trying it and experimenting around, but you want to get some guidance, read this paper because there's lots of debate on it. There's lots of debate from smart people, and there's lots of contradictory evidence in the sense that no general principle seems to apply. So give this a read if you're interested in that subject. And with anybody that's taken the workshop today, should be able to have a handle on what's going on in there. Maybe not a complete understanding of the paper, but certainly some of their arguments of where they're coming from. Okay, I'm glad you can see the cursor there. I can't always tell, and it looks really stupid if I can't tell you can see the cursor. So thank you for telling me that. Okay. The convolutional layers, as I mentioned, go from low level to high level. Another explicit way you can see this is what if we intentionally mix them up between images? And this is something that many of you have probably seen the outputs from, deep dream generators and similar types of code. You go to a website and just feed it your own photos, and I'll show you the Keras code for it in a second. So deep dream generators are a neat application, mostly a novelty application, but the way they work is they take the outputs from one image at a low level and mix it, which is called the style, and they mix it with the output from another image at a higher level, which is called the content. So the content of this picture is, this cat in the bushes, leopard here in the bushes. The style is a bunch of dice, and we can mix them together for dramatic and interesting artistic outcomes. Here's a bunch more of these type of images, which again, Deep Dream Generator is a web page you can go and play with these yourself. So you can make a photograph look like the style of a painting, and it does a pretty good job of it. And again, the idea is really it's just mixing the low level and the high level filters together. And so there's, I like these examples because they give you a very dramatic way to see that this is exactly what they're doing. There's a Keras example of this right here. It loads a pre-trained ImageNet model. So the nice thing about training this is that we'd like the model to start not from scratch. And so this idea of transfer learning or loading pre-trained models is something that makes sense. If you know that one of the components of a system that you want to use should be, was trained somewhere else by somebody, and training is expensive and could take weeks easily take weeks on expensive GPUs to do useful stuff. Well then, hey, wouldn't I like to leverage that model even if I'm using it slightly differently? Well, you can. You can do transfer learning. You can bring in things from that model. So you can save models and you can grab them. And this uses a pre-trained ImageNet model to get this thing off the ground. So training it is not expensive and painful. So that's an important capability to understand is out there. The other thing I was mentioning is that inference is fast. And that's really important to understand the impact and the deployment of these things in the real world. So that here, for example, people have lots of demos on, this thing won't probably activate unless I go back to not laser pointer. Let's see, in cursor mode. There we go. Now it's playing. So here's an example. This runs on an iPhone, recognizes object, can give them a bounding box in very much real time. This is even a couple of years old. And there are plenty of things like this. And an iPhone's pathetically underpowered for doing these kind of operations. It's limited so much by battery and heat dissipation, but it can do this. It wasn't trained on an iPhone. That would be incredibly painful. It was trained somewhere in a bunch of GPUs for many, many hours. But once it was trained, you can stick the inference part on an iPhone and it works in near real time. That's because the forward part, like I said, is nothing more than some matrix multiplies of your really clever, pricelessly trained convolutions. And this shows up in cars, for example. Self-driving cars rely on this fact. A very dramatic way to see this is that any modern car, but Tesla did a good explanation of this with their Auto Day or whatever they called it. I think they're going to do it once a year, Auto Driving Day, something. They did a presentation basically of their self-driving capabilities in their cars. And one of the things that they presented in detail, which was nice to see publicly instead of it being proprietary information, was that their hardware in that car has built into it. They've got a custom chip they built just for themselves to do their driving. And if we look at what it does exactly the kind of operations that you now understand. It's very good at doing matrix multiplies. It's got ReLU hardware in it, so hardware that does that activation function, and it's got pooling hardware. This is exactly the kind of things we just looked at. And it does nothing but that very, very fast. Well, it has some other processors on here, but this is mostly what it does. And it can do it at 72 trillion operations per second total, because it's doing these low precision, just these operations. So it's very fast in the forward direction. And that's how they hope to have Tesla cars become fully autonomous. And however good they are currently driving, that's how they can do it. They've got relatively low powered stuff that you can stick in a car. And it's pretty primitive electronics in the sense that can't be bleeding edge and require a lot of sensitive environment and everything. And yet it works well because the inference part is so cheap. So keep that in mind as you work on neural nets. Training's painful, but inference is cheap. And that is why people are rushing to do specialized hardware to help on the inference part. And they can then wrap this in the training engines around it. So NVIDIA, for example, on the GPUs that we have on Bridges, the latest ones, has tensor cores. And these do nothing but 4x4 matrix multiplications incredibly fast. They're mixed precision. So they're 16-bit fixed point precision. They can mix into 30-bit precision. The details aren't important. The point is that they're low precision matrix multiply monsters, because that's what deep learning is about. Google has their tensor processing unit, the same kind of approach. Intel is going a little bit more organized, like the hardware around doing the deep learning, the artificial neurons kind of approach. So they've got something that looks a lot more neuromorphic in that sense. And pure neuromorphic, people like IBM are doing, make the silicon look like a bunch of synapses connecting neurons. And that's because nature, again, has a lot to teach us. The human brain, which is going to take about an exaflop to model in real time, uses 20 watts. That exaflop machine that they're trying to build now is going to end up using probably about 30 megawatts. So that shows you how much better we can do. And nature gives us lots of hints. Like I said on the first slide or so, when I said there's a lot of biological inspiration, doing things like making these networks analog, pruning the low weight connections to zero. If it's not important, make it zero, just get rid of it. Lots of things like that. So there's a lot of stuff going on in hardware. And if you understand the software algorithms, you understand the directions the hardware is going. Okay, that leads us to a more practical matter of adding TensorBoard to your code. TensorBoard is this wonderful piece of the TensorFlow ecosystem. Another reason I picked TensorFlow is because it's got an ecosystem that's pretty mature, and its nearest competitor, which we'll talk about in a little bit, PyTorch, I don't think its ecosystem is quite as good, although PyTorch has learned to use TensorBoard too. But at any rate, TensorBoard is one of those pieces of the ecosystem that makes life much easier when you start doing real deep learning research, because we can get a lot of output out of our models without a lot of effort. As a matter of fact, all we need to do is to add into our model fit, we add in some callbacks. Callbacks basically are hooks into real time, into runtime. And if one of the callbacks we can add in is a TensorBoard callback, that will now capture when it's fitting the data. It will capture for us in real time some information, and it'll write it out to a disk so the TensorBoard server can see it in real time, so we can monitor whether you want to do it real time if you want to monitor things and say, I'm done training here, or whether you want to just use it after the fact. TensorBoard gives us a lot of capability that all we need to do to activate it is stick in this callback right here. You give it the name of a logging directory that you want, how often you want it to capture this data, and stick it in here as a callback. Boom, you're good to go. Now, it does run as a server, so there's a little bit of overhead to it. Somewhere else, you need to start up the TensorBoard server. This looks at that directory in real time, looks for information to appear there, and it will post it. And anywhere else now, so this can be something, if you were on Bridges, this can be something from your browser at home. You just make sure that using port 6006, you point it at the right server. That would be Bridges if you're using Bridges. For many of you, if you're running it on your own local machine or your laptop or whatever, it'll be localhost. But at any rate, you can point your browser, your web browser at this port, and it will start to pull up the nice UI that looks like this. So here's what TensorFlow does for us automatically. These are the kind of accuracy graphs that we were drawing ourselves in Matplotlib. We can get those automatically from TensorFlow. This happens to be our first model, which is our 64 neuron wide fully connected network. So here's our accuracy and our loss. Here's our CNN network, which we can see did much better. We don't have to plot these ourselves anymore. So TensorFlow, it's one of the things that we'll do. It will also do this in real time, as I said. So if this thing takes many, many hours to run and it starts over training early on and you go, okay, well, those aren't good hyperparameters. We learned all we can learn there. You can monitor it and say, time to call it a day. It allows us to also drill into the architectures we're looking at, which sometimes if you're deploying a model that somebody else has written from some code, as we're about to see, the architectures can get quite complex these days. So it might not be so important with our models, but with some models we're about to look at, they can get complicated enough. It's nice to be able to pull up a graph of it. And you can drill in to the graph as well and look at it in more detail. Also with Keras, TensorFlow works nicely with Keras. It can pop out an even simplified conceptual view as well. So here's our CNN's conceptual view, which we know very well. Convolutional layer, max pooling layer, dropout. So very, very simple diagram of it, which for more larger complex networks might be a nice thing to verify as a sanity check. More sophisticated kind of thing it can do, and we don't want to do ourselves in Matplotlib if we can avoid it, would be to start to show us the time evolution of our weights and biases. And so we can see as the model evolves the way things are happening here. We can tell if things are they exploding or are they vanishing? Do we want to do batch normalization somewhere? So we can look at a lot of these parameters. We can also see histograms of them here, which is an even more detailed way to see it. So we can get a handle on some of what's going on. Now, if you say to me, oh, what's the magic exact thing we want to look at that tells us something in particular? No, this is a tool that needs to be applied with some sophistication and knowledge on your part. You need to, there's no thing here that's a signature of things are going completely wrong. How do I know it's exploding or vanishing? There's a lot of context to that. What should you expect for values? So you do need to have some understanding of what's going on, but when you have that understanding, it's nice to know that you can actually get the feedback that you need to apply that, or to push you at least as the kind of understanding you might need to go and gain in a fairly painless way. There are add-ons to TensorBoard that are quite nice. For example, hyperparameter search. As we've said, hyperparameter searching is a huge part of the effort here. TensorBoard allows us to set up some nice search space kind of strategies here and to get some feedback automatically. So TensorBoard, we can run these different models with these different hyperparameters here. So in this case here, we can see the number of units we're varying, the dropout varies, the optimizer varies, here's the accuracy that comes back, and it can help us to automate this. Performance profiling can become quite important once we start worrying about why things are taking 2 weeks to train. Well, does it have to take 2 weeks? Or maybe if we did something smart, it could take 2 days or 2 hours. Well, how do you know that? Well, you can get a clue by starting to drill into where the time is spent. And TensorFlow plugins can allow us to see this optimization. Sometimes you only want the basics, like how much time is spent on I/O. I/O, for example, can easily be where a lot of time is spent because we're reading these many samples. And if we're reading them stochastically, right, we're doing stochastic batches, which means every time you go out and grab one of your million image samples, you want to grab a different 10,000. So you're all over this disk system grabbing images. And that can be very expensive. Now, there's lots of ways to mitigate that. For example, you can grab the next batch in advance while you're training. That's an obvious smart thing to do. And using the right I/O routines will do that automatically for you. Let the CPU do the work in the background where the GPU is chugging along with back propagation. Let the CPU grab the next batch of images, maybe do some pre-processing on them, get them formatted. So there's things you can do, but first of all, you need to know you have a problem. Performance profilers can give you some slicing and dicing on the time. And if you want to get into the integration of the hardware-specific tools, mostly NVIDIA tools, the NVIDIA tools can integrate nicely because NVIDIA really does own this space more than anybody. So the NVIDIA tools integrate into the level that allows you to really dive in and see exactly where your GPU time is going, routine by routine, kernel by kernel. And you can really start to see if you're doing the right things or should be doing something else. So there's those options, though, are made much more friendly and accessible by TensorBoard. Let me see if there's some questions.
Any questions?
Can you elaborate on somewhere else for starting the server? Yeah, somewhere else means, you know, if you're running your model in a Python shell, you want to start the server up, you could start the server up in the background beforehand if you know how backgrounding stuff in Unix works, or you could just open a separate window. As a simple way for many of you that maybe less, open a separate window and run that TensorBoard command and make sure you're sitting in the same directory that your Python script is outputting data to. So that's probably the simplest way to not go wrong. So by somewhere else, I mean, once you're inside of a Python script and it starts running, how do I start TensorBoard up? Well, it's too late then. So you want to start TensorBoard up either beforehand and before you start your Python shell and run it in the background. In Unix, that could be as simple as ampersand, but maybe that's also using computing resources. Or you want to start a separate terminal window, start TensorBoard. You can even do it while your code's already running. So that's what I mean by somewhere else. You want to start the server. Can't do it in the middle of your Tensor training happening. Let's see. And connecting to bridges, we actually have specific instructions on using TensorBoard with bridges for those of you that are interested. So you should go under our software page under TensorBoard. We have a software page for TensorBoard. It will step you through the instructions. I think it gives even a couple ways to do it. So please take a look at that page because there's a couple details, and if you don't get them right, you'll bang your head on the wall for a time, and that's not necessary. So take a look at the TensorBoard software page. Okay. We're going to do a comparison of TensorFlow with Caffe and some other frameworks in just a couple of slides on the same system. Yeah, so TensorBoard needs to be on the same system so it can read the files that are being output by your training. I said same directory just because you give it the name of a directory. That makes it simple, but you give it the name of a directory. You could give it the full path and start it from anywhere. As long as when you give it the name of the starting directory or the logging directory, everybody's on the same page. You just need to make sure TensorBoard can see whatever you've told the Tensor runtime hook to log to that directory. It's that simple. Okay. Let's see. We're getting close on time here. I got to keep moving here. I don't want to leave time for questions. Scaling up. We can scale up to multiple GPUs, and these days that's almost required if you really want to do any kind of leading edge research. If one GPU is good, well then lots more is better and certainly can speed things up. Now the question you have to ask yourself when you're using multiple GPUs is how do I get them to all cooperate? The early primitive approach was to do this ensemble approach that we mentioned briefly before, which is to say, let's have each GPU do its own independent training and learn things, and when we're done, we can have them vote on what the correct digit is. The problem is, that means when you're done and you want to use the thing, I still need 3 GPUs to vote. And I'd rather have my multiple GPUs instead spend their time training one model that's really good so that I only need 1 GPU or 1 iPhone or whatever in the future to run my model. So I'd like them to cooperate on training the best network instead of having 10 of them train 10 okay networks that have to vote. And so to do that, though, we got a little bit of trick because how do we have them all train the same network? It means, well, what it means, the solution is what we have them do is they start out with the same model, the same weights, the same network. They train on different data. They look at different data. Now they all end up with a different way that the optimizer would like to adjust the weights because they've all seen different data. So they all want to adjust the weights a little bit differently in back propagation. But what we do is we don't let them do that. We just instead average all of their pushes. And their average is kind of like them voting then on which way to adjust the weights. Then we adjust all of their weights simultaneously with that averaged push. So they all stay every cycle using the same weights as they go through the training cycles. But that means they need to coordinate to average things. And that takes a little bit of effort and takes some communication bandwidth between them. Fortunately, TensorFlow has that capability built in. If we just use the mirrored strategy built into TensorFlow, it's not hard to hook into. You can see minor adjustment in our network here to add that in. Now we have a multiple GPU network. You can train on multiple GPUs. However, if we want to start training across a huge distributed machine, like using all the GPUs on bridges or thousands or tens of thousands of GPUs on some of the world's biggest machines out there, like the DOE machines, Then we need to scale up beyond this strategy. And the best thing out there at the moment is Horovod. Horovod's been used to scale up to 30,000 GPUs, and it basically does the same strategy, but it has a little bit more framework to it. Not a ton. As a matter of fact, here's MNIST with Horovod, an abbreviated version of it. I cut out a few lines to fit it in here, but you know what the lines are. Here's a Horovod framework that would allow MNIST to train then on 10,000 GPUs. That'd be a ridiculous waste for MNIST, but it does relate to, it shows you exactly how to do it with what you already know how to do. So that's why I find it to be useful. As a matter of fact, here's the application that motivated the development of Horovod, is running at 1.1 exaflops of mixed precision, so low precision, but still a tremendous amount of computing on 27,000 GPUs. They did some weather event prediction on all those GPUs. Here's the network design. I hope now you're actually capable of making some sense of this. You can look at this and go, hey, I know what these layers are, convolutions and pooling and more convolutions. You know most of what goes into making this thing work, at least at the building block level. Okay, let's talk about, since we're running out of time, we wanna take what would normally be some day 3 material. If we had a day 3 here, which we don't have, I think about a day 3 a lot, but I appreciate the fact that you found time in your calendar for 2 days. That's tough enough. I think 3 days, people tell us, might be too much for people with actual working schedules to find. So much as I'd like to have a day 3, it's hard to justify. Give us that feedback again on the evaluation forms, because that's what allows us to decide if we ever want to do a day 3. If we had a day 3, we'd start to dive into some of these other applications that we could do. But even with MNIST alone, digit recognition, we can do some other more interesting things. We did classification. We looked at digits and said what they were. But we could do localization or detection or segmentation, which means, hey, where are these images in the picture, if there are any? Which, for example, a lot of turnpike toll booths these days, toll booths for highways, they just snap your license plate and automatically bill you. And the way they do that is because they have a neural net, a convolution neural net that can basically find the digits in the picture of your license plate and recognize them. So we could step up to that level and be able to recognize digits in more complex scenarios. This would call for some different network designs that we've done, and this is where we'd start with day 3. So we don't have day 3, but I can go over the pieces that would make up day 3 for you, because they're not a bridge too far for you to understand if you understand the layers that we have gone through, fully connected and convolutional. They're kind of nice evolutions of these: residual and recurrent, long short-term memory, transformers, which are attention-based. We can get into these. And some of them, like restricted Boltzmann machines, are pretty much just textbook theoretical stuff, but some of these are widely used and good to know. So let me see, before I charge too, I'll take a quick pause for questions so don't pile up too much. Let's see. How would you compare TensorFlow Cafe? We'll come back to that. That's ahead of us. Clarifying tensor boards, same very, going back to an ensemble question. Single trained on 3 GPUs typically outperform 3 single models trained on 1 GPU each. Single model. In this case here, okay, that is an interesting question here. The training times differ, so it's not fair to compare them head to head. I mean, you would guess that the ensemble training in general is going to be worse than you can get out of a well-trained single network because of the question of multiple overfitting. But it's a trickier question to answer than a yes or no. It could go either way, and it's also tricky to answer because you have to say training time. Training time on the 3 ensemble ones is going to be not impeded by having to do synchronization and communication. So, and it might train earlier, quicker because of that. So it's hard to just say yes or no on that question, but it's an interesting question. Okay, residual neural nets. We've talked about disappearing gradients being an issue if we make very deep convolutional networks. And yet the convolutional networks I've shown you a couple of briefly, we flashed before, you have a lot of convolutional layers, right? So how do they deal with that? And the answer is not just batch normalization. Instead, the answer turns out to be a fairly simple idea, actually a simple implementation of what about some feed forward in our networks? What if instead of just having this particular layer pass through to the next layer and in the process maybe damp some of the gradients, what if we skipped some of that entirely past the layer and add them together? So it's a little bit of feed forward, just like an electrical circuit if you had some feed forward around the signal. And this does help us preserve gradients, right? It forces some of the gradient downstream. And this turns out to be very effective imagery-based stuff. Also some non-imagery-based stuff like AlphaGo Zero, which became the kind of superhuman Go machine. It's 40 residual CNN layers. Well, it needs the residual part to make 40 layers work. We can go to hundreds of layers with this. And here is actually some TensorFlow code to implement what could be a residual, what is a residual layer. We can basically say, Here's our input, here's our convolution, and here, before we go to the next layer, let's just add the two together, add our input and our output of this layer together. And Z is what we pass along to the next layer. There you go. That's code that actually implements a residual layer. So we can do that without a lot of great effort. But however, this does raise the question now, everything we've done so far was sequential layers, one after another. We're starting to get into layers now that maybe aren't so directly sequential, or that can even branch out. We'll look at a few now that branch in different ways. And that's not hard to do either. Just instead of sticking everything in a sequential region like we've done, Keras supports a functional API that allows us to define branches. And then we can define where the branches concatenate with each other. And it's very straightforward. It's not difficult. You can see MNIST here with implemented with the functional API with 3 dense layers, but you can see the functional API. It's not difficult at all to use. Let's see. Here is an example of a 15-layer CNN to do MNIST. And it's silly. It's not effective. It's not a better way to do it. But if you want to see how you can do MNIST with 15 convolution layers without being destroyed by vanishing gradients by using recurrence, there you go. So again, it shows you recurrence in an application where it might not be the wisest thing to use, but it's the only thing that makes it even work with 15 layers. Okay, well, if feed forward is a good thing, how about feedback? Does that have its place? And indeed it does. Feedback is extremely useful because feedback gives us the ability to start to have some context in our problems. Context is incredibly important for any kind of intelligence, artificial or otherwise. Our MNIST characters are just pulled out of a batch and we look at them and say, that's a 4, that's a 2. However, most character recognition you do in the real world is in a context. You're reading something and that's how your brain is good at it. As a matter of fact, here is a classic little kind of trick to show you how good your brain is at figuring out context. If you can read this paragraph, you're miraculously figuring things out from context because any given word here is completely gibberish, right? And yet most of you, I'm sure probably all of you, I hope, can read this paragraph just fine, right? It's a good example of how important context is to when your brain is actually processing text. Here's a little more directed, simple example. If we've got some text like this and we're trying to do character recognition on it, and we see the dog chased the cat up the tree, it's very easy for us to tell that this smudged digit is an A because it's got to be cat, right? There's no other word that makes sense here. It's not caught, that doesn't make sense. Cut, that doesn't make sense, right? So we can easily, from context, infer what this digit is, even though reading character by character, digit recognition scheme, or indeed ourselves, if we had a little sliding window here and just had this A, it would be hard to tell. So context is very good. Recurrent neural networks, by having feedback, let us look at some recent things we looked at. Matter of fact, the one way they're typically presented when you first look at recurrent networks is we can kind of unroll them out in time and look at past time steps. We can unroll them out and say, oh, we're looking at previous samples at the same time we're looking at our current sample. And so this is a way of unrolling things in time. So it gives us some context. As a matter of fact, that's such a good idea to have context that people said, okay, well, if memory is helpful, how about if we actually implement memory? And indeed, the long short-term memory idea, LSTM is the abbreviation you'll always see, was first proposed by Schmid-Huber, a guy whose name will pop up again and again, back in 97, back before there were lots of practical high-performance networks to implement it. And it's taken on many variants since. And this is, I like to tell beginners, emphasize this to beginners, because if you think that LSTM is a particular design, it's not. There's a lot of different ways of implementing it, trivial details, but they're important. So LSTM is not by itself a complete definition. There's a whole paper I find useful to explain this, how many variants there are. But at any rate, the basic idea is that we now have a memory cell at our neuron that can remember stuff and can also forget stuff. That's important too, is to be able to purge it and never forget things. And that gives our ability to remember in time a lot more depth. Recurrence can only go back so far, whereas a memory cell can go back, well, infinitely far if we want to remember things. And that means it can remember longer sentences. It can go back further in sentences than a few letters, maybe. You can go back many words and help use that as good context. It is, once again, a very simple thing to implement in Keras. The entire complexity layer is taken care of for us, although it has lots and lots of options, because as I said, LSTM can be implemented many different ways. But the layers to do it are very simple and straightforward. We even have an MNIST version in Keras, if you want to look at it. Now, the way that it's actually implemented to do MNIST, I think, is confusing because It's really, as I said here, killing a fly with a bazooka. So they really had to contrive very hard to make this work with MNIST because it doesn't make a lot of sense to use on that problem. So if you care about it, I would maybe not suggest focusing so much on this. I find it confusing. Instead, I'd recommend, here's a much more natural problem. Here's a network. It's not that complicated, but it's also in the Keras examples. So it's meant to be a beginner kind of thing. It uses the network to predict the next frame of an artificially generated movie with moving squares. So this thing looks at movies and sees where the squares are going and tries to figure out where they're going to go next. That is more appropriate for LSTM. LSTM, as you can imagine, is very useful in a picture. Say I've got a picture of a horse running around in a field and I'm trying to do analysis and I recognize the horse. Well, if 1 frame ago, if a 60th of a second ago, the horse was 2 inches over, and now I've got a 60th of a second later frame, I got a pretty good idea where that horse is going to be in the picture and how to begin to look for it. So that's where context is very, very useful, and LSTMs can be good. As a matter of fact, context is so useful that it can be useful sometimes in 2 directions, especially in text analysis and natural language processing. For example, let's say we have this sentence that we're parsing right here. The dog chased, and then we got a digit we're not so sure about. Is this a car? Is it a cat? What is the dog chasing? Well, if we have the rest of the sentence, the dog chased the cat, the whatever up the tree, it's obvious in this case it's not a car, it's a cat, right? So having bidirectional reading of the sentence can be very useful. And we can do this with a bidirectional LSTM, which once again is a trivially easy layer to plug into Keras and can be very good. So for things like the IMDb sentiment analysis database. So built into Keras, one of the data sets you have at your fingertips is a bunch of movie reviews, and the challenge is to figure out if they're positive or negative. Did they like the movie or did they not like the movie? That's sentiment analysis. And this is very relevant stuff. I mentioned yesterday that analyzing tweets right now to find useful stuff about COVID propagation. Can we tell where people might be getting sick even though they don't know it, or where clusters could be outbreaking? That is a version of sentiment analysis. You're mining tweets to figure out what the context is. When the IMDb movie case is a very straightforward example of that. It's built into Tensor dataset. And here is how you can implement a network that does that well. It first needs to process, embed, or figure out a way to represent the words. Once you figure out a way to represent words to feed a neural network, then we can do this bidirectional LSTM. Very, very powerful, sophisticated technique, which is a couple of Keras statements. And then when we're done with all that, we feed it into a dense network with some dropout. And on the output here, we figure out good or bad, yes or no, positive or negative movie reviews. Now, this comes back once again, our dimensionality reduction flag pops up because this concept of word embeddings leads us to the idea of dimensionality reduction. Once again, we're going to take a huge vocabulary of maybe 1,000 words and try to figure out how to represent it in a smaller space, because we don't want to have 1,000 different words, figure out how to input those into a neural net. We might want to be able to fit them into a smaller space. In this case, our embeddings input is going to figure out how to take each word and reduce it down to a 64-dimensional vector. Well, let's talk about embeddings in a way that you can absolutely 100% understand now with your understanding of just dense neural network layers. And autoencoder is a fantastic way to introduce you to this concept besides being an interesting application. An autoencoder is where we take and we train a network on a set of inputs to generate the exact same outputs. And at first glance, that sounds like an incredibly stupid thing to do because what good is that? But it turns out to have some really interesting capabilities implicit in it. So if we were just to do this, train this network to output the same inputs like this, it actually wouldn't be interesting because it would just learn to pass everything through as the identity function. What good is that? The answer is no good. However, let's say that we force the network down into a narrow waist like this, fewer neurons on the inside like this. Now, what we're doing in this process is we are forcing this network to somehow learn to reduce the representation, to go from a higher dimensional space to a lower dimensional space in the middle. We're forcing it to do that. So we're forcing it to encode somehow these faces. Then on the other side, it's got to get from this low dimensional space back up to the full dimensional space of the pictures. That's a decoder. What that means is in the middle here, we are learning latent features. Comes right back to us from our movie review and our movie recommenders, right? The latent features here becomes a reduced representation of these faces. We're forcing it into this. So these latent features give us an encoder and a decoder and give us a way of squeezing down our highly dimensional picture space which if it's 1,000 by 1,000 image, right, is a million dimensional pixel space, we can squeeze it down into a smaller space, which somehow compresses those faces down to the features. And this autoencoder concept is very foundational. It's used in generational networks. So we've so far been looking at things that mostly recognize stuff and don't generate pictures so much, although we've seen some examples of it. But sometimes you want to generate things, new faces, new images, like Deep Dream is generating new stuff. Generational networks need this kind of decoder aspect to them. We can make variational autoencoders by controlling the latent space in the middle of these pictures. If we start to put some constraints on it, because normally the latent space is just learned to be whatever it wants to be to efficiently do the encoding and decoding. But if we start to squeeze it down and insist that it has some kind of distribution, we can start to get some control over that latent space. And we control with a couple, instead of having one vector there, we have a couple vectors that represent the distribution in space. We can now actually maybe get some handles in there that begin to represent things like facial features or pose direction. And maybe we can even get some control so that in that latent space, we can turn on or off blonde hair or glasses. Indeed, that's what we can do. Or it can even be the input into some more complex stuff like we saw with our previous bidirectional LSTM or designs like transformer networks. So that we can get the encoder concept's important, but where it's most obvious and where you can use it with just what you know right now at convolutions and dense networks is deepfakes. Deepfakes have great significance right now because they have such potential impact on trustworthiness of what we see. And a deepfake works like this. We train an encoder to look at faces of Alice, and we train a decoder to decode Alice. So it's just an encoder-decoder network, nothing particularly fancy there. But we also train that same encoder to recognize Bob, but we switch in a different decoder for the Bob images. So one encoder learns how to compress both Alice and Bob, whereas these two decoders only learn to take these latent features and turn it into Alice or Bob. Well, now what happens if we take Alice on the input side and then we stick Bob's decoder on the output side? What's going to happen is Alice is going to start being able to puppet Bob. Alice's pictures or poses or facial expressions can move Bob. So, and we can do this in real time, or we can do it with video, so that Alice, with her video clip, can recite the Gettysburg Address, and Bob over here is going to end up looking like he's reciting the Gettysburg Address. And that's how deepfakes work. That's exactly how they work. Here's a demo. I won't spend any time on it because we're really getting pressed for time, but you can go to it of the Chinese app Zhao, which takes a photo and in a few seconds has Alan Zia in this case here, does a great job of imitating Leonardo DiCaprio in some famous movie clips. And it's, it's very realistic and hard to tell apart. Well, I'll skip that demo both for volume purposes and because I don't have time, but you can play it yourself. Okay, what I really want to squeeze in here though are architectures, because we've started to look at all these layers. You combine these layers together, you start to build these big architectures. And as a matter of fact, once architectures are good at something, you can even use them, the entire building block, entire architecture of a building block in a larger, more complicated network. And so a couple examples of that are GANs, generative adversarial networks. They're very popular and important right now. I'll quickly go over the concept again. If I had a day 3, this would be a fun thing to dive into. The idea with a GAN is that if we take a network and we train it to recognize, say, cat images, and it says cat or not cat. It's good at recognizing if something's a cat or not a cat. And we train it a little bit at that. I think it's good at recognizing cat or not cats. What if we take another network and we train it to draw cat pictures? And at first, it's terrible at it. Matter of fact, the cat pictures look almost like noise. So the cat picture network's terrible. But we have the cat network that's learned to recognize real cats start to give some feedback. It says, that's not a cat. That's not a cat. But then it says, that could be a cat. So we have the discriminator network tell the generator network if it's good or bad. And as a result, the generator networks get better at drawing cats. Well, now some fake cats start to get through the discriminator. The recognition network that's supposed to recognize cats gets fooled. Well, we can give it that feedback so it gets better. I fooled you. Well, okay, well, I learned you're not going to fool me again. So these two in an adversarial relationship get better at drawing cats and at recognizing fake cats. And as a consequence, we end up with a network that gets good at drawing cats. And that is an interesting goal. You've taught a network how to draw cats that don't exist. It's not just going to draw cats that exist. It can draw all new cats that didn't exist before. So That's one thing you can build out of building blocks that we already know. Here's another one that's a good example of doing recognition and segmentation of images. So we built this up out of a bunch of convolutional networks that were in themselves successful at recognizing things. And now combining them in a certain way gives us much more power. And indeed, that's why mask R, CNN, if you look at the architecture built up of these pieces, is really good in real time at doing a fantastic job of recognizing things in an image. So for example, it knows this is a knife. It knows it's a knife with 83% confidence. It draws a bounding box. Where's the knife? And as a matter of fact, it can even draw each pixel of the knife. It can segment the image. And it does this in real time very fast. So we can do some very sophisticated networks by building them up in blocks. And today, that's how a lot of networks are built. Okay, that leads us to another subject. Doesn't actually lead us there. This is kind of a jump in a different direction, but an important topic, which is data augmentation. All of these labeled supervised learning techniques require data. The data can be very expensive. And so you'd like to have more data somehow for free. One way you can do that and make your networks better is by augmenting the data you already have. That means basically taking your data and somehow perturbing it to make it look like new data. In the case of MNIST, we could very easily make our network better than it is now by, instead of having every label be a nice, well-oriented character, we could shrink and enlarge the characters without any effort. We can do this automatically with some batch process. We can rotate the characters. We don't need to have a human go back. We know this was a 5 before, it's still a 5. We just shrunk it. We can now have digits that are rotated some. Our network's very poor at recognizing rotated digits because we didn't train on any rotated digits. We can introduce some noise in here, make it better at fuzzy things. We could slide the images around for translation invariance, which, by the way, usually with convolutional networks you get for free anyway. But at any rate, we can see how some straightforward mechanical messing with our images gives us a lot more data that we can now use to train our network and make it more robust. So this is called data augmentation, and you'll find this technique is employed in almost every research paper because labeled data is expensive and we'd like to make our networks better anyway. The TensorFlow image stuff gives you a lot of components to make this process very convenient. So if you use this class, you'll go and look on the API, and it's got lots of things to do exactly this right there. So you don't have to go and write your own pipeline for image processing. But this leads us to some things besides supervised learning. So supervised learning is how what we've been doing with MNIST. It's how you learned colors. Your parents said you said green. You pointed at a fire truck and said green, and your parents said no, red. And so you learned the difference in colors. But this requires labeled data. And as we said, that's expensive. On the other hand, you could learn from no unlabeled data. And you say, how could we do that? Well, we actually have already been doing that. When we did our clustering yesterday, or our recommender system, we didn't have labeled data. We learned things from implicit structure in the data. We found clusters and figured out how things were clustering without having our data. So you can learn from unsupervised data. And there's yet another different approach, reinforcement learning, which requires long-term goals. So you don't have something right there saying yes, right, or wrong. Instead, we have a long-term goal, and we have to learn how to do things that get us to that goal. And typically, it means you're not just reading the data, but you're interacting with it. If you're learning to play a video game with a deep learning network, it's actually interacting with the data with the video game. So these are all 3 separate classes of learning. They've all been done with and without deep learning, but deep learning has really kind of taken over all of those. And the field of deep learning, though, is very much a theoretician's nightmare. That's not my opinion. That's from a guy who's been the godfather of deep learning since the 80s, when it was a dead end for many perceived to be. Because it is very difficult to analyze these interesting techniques theoretically, but that doesn't stop you from being able to do it because you can experiment with these toolkits I've shown you. My own opinion is this looks a lot like late 19th century chemists. I'm a physicist by heart, so I understand the history of chemistry and physics and how quantum mechanics came into chemistry and the table of periodic elements. And I realized that before there was good theoretical understanding of chemistry, the chemists still did a lot of fantastic stuff, but they had to do it because through empirical methods rather than having a lot of great theoretical guidance. But they still did great stuff. It's the foundation of a lot of modern chemistry and products that we use today. So you can make great progress without the theoretical foundations being in place. But that does mean you're going to need to do a lot of empirical testing. So I've given you one toolbox, TensorFlow, and in a sense, Spark to work with it, but some other toolboxes that are out there. Let's quickly look at them. So TensorFlow is, I picked it because it's very friendly, particularly with Keras, and very popular. Caffe was popular for a long time. You'll find it in older research papers from, say, 5+ years ago. It was important. It got absorbed into PyTorch and has kind of now disappeared as an independent network. It's part of PyTorch, basically. Spark has machine learning stuff built into it that we've already used, like clustering and whatnot, but it doesn't have deep learning built into it, but it has frameworks that allow it to hook into TensorFlow very easily. Matter of fact, it's got multiple ones. So if you're interested in using TensorFlow within Spark, you can find these plugins right here to allow you to do that kind of stuff. I suggest in most cases, though, TensorFlow is best used pipelined with Spark instead of within it. But sometimes it is useful to use within it, especially if you do want to integrate, say, a testing harness outside of TensorFlow to run through lots of parameter iterations and whatnot. We saw how TensorBoard can help with that, but it can also be done in TensorFlow. Scikit-learn can also help with that to some degree. There are some other frameworks that have since kind of fallen by the wayside or used at low level, but the other one that is popular that rivals TensorFlow is PyTorch. When it was originally Torch and you needed Lua to use it, it wasn't so popular. But once it got a Python wrapper, it became quite popular. It used to have the difference between it and TensorFlow, where TensorFlow was much higher performance, so people that were interested in real production networks used it, whereas PyTorch was better for experiments because it had dynamic graphs and you could do things interactively as you used it. Now with TensorFlow 2, that gulf has kind of disappeared. PyTorch has a little bit better performance, and TensorFlow now has much better dynamic graphs and eager execution, so that they have less of a gulf between the two. And as a matter of fact, I'll show you some differences here. TensorFlow 1, just so you can go back and look at this later, used to be lower level. That's why TensorFlow 2 or PyTorch was considered friendlier. You can see Keras now has taken away a lot of these details here. Here's one layer that we're now replacing with just our convolutional 2D routine. It used to be a little bit more lower level detailed. In our previous workshops, I kind of exploited that to explain the lower level details, but it certainly wasn't as friendly to use. Now, with PyTorch, you can see here's how a network looks, the layers in PyTorch. Here's the closest example I could find. I wasn't willing to go and code one up in PyTorch myself, but I grabbed one for MNIST. There's lots of them out there. And here's convolutional layers with pooling and dropout in PyTorch. And you can see it's very similar. It's not difficult to, this is not a fair comparison. All this extra code in here is the person who wrote this example wanted lots of testing options and whatnot. It'll read in parameters and stuff. So it's a lot more flexible. It doesn't need to be this overblown. So it can be pretty small and terse too. The real guts of it are here. And you can see this is comparable to TensorFlow. So if you understand one, you're not going to be lost looking at the other. Scikit-learn, on the other hand, is a framework that's intended to do. It's something you can put on, you probably should have if you do scientific stuff on your laptop. It's got a lot of the pieces of classical machine learning built in place on it. It's fantastic for that. You can combine it outside of TensorFlow and use it to control some TensorFlow testing of hyperparameters, although again, TensorBoard these days makes that a little bit easier. But Scikit-learn does bring us back quickly to a topic that I think I can't overemphasize enough, dimensionality reduction. So in TensorFlow, we could do MNIST. We could try character recognition, which is pure dimensionality reduction and clustering. And we can see how far we get. Scikit-learn, if you've got it installed, has a data set already built in. That's not quite MNIST. They're even cruder characters. They're 8 by 8. So they're very low resolution characters. They make our 28 by 28 characters seem high res. It's got 8 by 8 character set. You can load it in with Scikit-learn. Here's some simple code I put together to show it. And if we try to do dimensionality reduction on Scikit-learn from 8 by 8 characters means it's in 64 dimensions, right? It's a 64 dimensional space. And if we try to just project that down to 2 dimensions, do some clustering randomly, we get noise. That's what we'd expect. These are random characters. But what if we use that principal component analysis technique we had yesterday, and we apply that and see if there's some structure, some arrangement of these characters? If we do that, we can find that our characters, which we can see are grouped by color, our zeros are one color and our ones are a different color, all of a sudden some real structuring appears here. And we might think that we might be able to actually cluster and use PCA and clustering to do MNIST, to recognize digits. Forget the deep learning. We're going to use clustering dimensionality reduction to get digits. And with principal component analysis, we get this far. It gives us a hint, there's a clue. Turns out we need some more sophisticated techniques to separate the digits, but we can do it. And here's a very sophisticated, interesting technique. It's got a lot going on it. But in TensorFlow, it's one line for you to call it and leverage it. The inner workings are complex. But yes, indeed, we can, by using dimensionality reduction and pulling things apart on the manifold, a higher dimensional manifold that the characters live in, we can pull the digits apart pretty successfully. So once again, dimensionality reduction underlies a whole lot of this stuff. You can't appreciate that concept enough. Here, I will, getting close to the end here, I will give you the exercises you've probably all been waiting for, because the good news is there are fantastic exercises for this deep learning stuff here. One very obvious next step is the fashion MNIST data set. And the fashion MNIST data set is meant to be kind of a drop-in, more challenging problems. As we've mastered MNIST, but we don't want to, we'd like to do something that's very similar, but more challenging enough that our 98% is not going to come for free. We're going to have to earn it. We can look at the fashion MNIST data set at 60,000 training images and 10,000 test images of 10 types of clothing in 28 by 28 grayscale. So it looks like this. And it's up to you to see if you can recognize a t-shirt top from a sandal or a boot or whatever the categories are here. So these are once again in the Keras data sets right there at your fingertips, and you can drop them right into the MNIST stuff that we've been using and see if you can get good results with different network architectures and different setups here on a more challenging problem. So that's a no-brainer to move on to next. But in the Keras data sets, again, a reason I like Keras, it's got built-in data sets that are ready for you to attack with some successively more complex problems. We have the Boston housing data set. These are housing prices. We talked briefly about those yesterday. Here's a real data set for you to work on. Housing prices based upon a number of factors. Can you predict housing prices well? If we want to get better with images still, the CFAR data sets give us some much more realistic images. We've got 32 by 32 color images in 10 classes, or 32 by 32 color images in 100 classes. So things like lawnmower start to come into play, and you can move up to that. If you want to jump off from here, you could jump all the way up to ImageNet data sets, which are higher resolution and again 1,000 categories still. So it's a nice evolution if you want to work on more complex problems. I already mentioned the movie sentiment database. Here it is at your fingertips. And related to that, but more complex, is this Newswires database. It's a bunch of stories that you can try to figure out the topic of the story from as text analysis. So for those of you interested in natural language processing, you've got some problems right at your fingertips. However, the best news of all in machine learning is that we have endless exercises available in competition-based data sets have been, as you've seen time and time again, the foundation of people making progress at the research level, and that has evolved into a wonderful community of competitive data sets and challenges out there. And Kaggle.com has done a great job of gathering those in one place. So if you go to Kaggle.com, you will find over 20,000 data sets across just an incredible, astounding array of different types of subject areas. I want to begin to list them. You can just see a smattering of them here. And at any given time, lots of competition, some of them with some serious prize money. So when I snap this, if you want to earn yourself 120,000 bucks, you should become the best at recognizing still defects detection with image recognition. But in there, you'll also find at some point in time, MNIST character recognition running. So we've got lots of competitions, lots of data sets, lots of successful winners from past competitions whose code is there for you to look at. You can't find a better place to find exercises like this that potentially relate to exactly what you're interested in. So please take a look at Kaggle.com. I have some demos here, but we've hit our limit on time. Steve may or may not cut us off soon, so I'd like to turn it into a question session and say the demos and whatnot are there for you to look at later. I think some of them are interesting, but we just don't have the time for them because I don't want to get, I'd like to jump into questions. Let's see what questions I have pending here. Maybe we do have some time. Let's see. How would you compare TensorFlow with Caffe? As I said, Caffe has been more or less absorbed into PyTorch, so as a standalone framework, it's kind of passé. Just clarify TensorFlow, same thing. Go back to Ensemble question. I answered that question earlier, trying to develop inverse imaging solutions. GitHub repositories for super resolution pet sensing. Google is really your friend on these kind of things. If Google can't figure it out, I don't happen to know of the best repository of all for data sets is this Kaggle one I just pointed you at. But there are many things that aren't gathered in Kaggle or scattered around. But Google's pretty good at ferreting them out in my experience. So that's your best bet is to start Googling around and finding things. And GitHub is not a surprising place to find lots of data sets either. But for your particular request there, no, I don't know of a place. But take a quick look around Kaggle. And although Google picks up that a lot too, and then look elsewhere. Okay, it's possible to use bridges in the future. It is absolutely, you have your accounts for the next 2 weeks. And if you go back to my first lecture, Startup Grant will buy you another year of usage for a 5-minute application process. So yes, it is absolutely possible to use bridges in the future. I encourage you to do so if you want to just continue with all the software and pieces that are there instead of having to build your own and grow things up. So go right ahead, apply for that startup grant. Again, it's a 5-minute process, it's very straightforward. But even without that, you still have a couple of weeks, or as Tom clarified yesterday, you have until your fellow students exhaust the account. We've only given so many service units to use for this workshop. So if somebody's a jerk and starts burning them up a whole lot, you'll have less time. So hopefully it lasts at least a couple of weeks. That's typical, I think. But again, startup grant is your real answer if you want to use bridges. Go apply for one now. You will have it. You'll be running tomorrow. Okay. Okay, with that, I have no pending questions here. So I will quickly then go through these demos until Steve cuts us off, and even if it doesn't cut us off, I won't go more than 5 minutes or so because, again, I respect your time here. So I'll quickly mention some of the demos I think are interesting. I've mentioned to you that having recurrence gives us some memory. Well, we can do amazing things with that, like look at a very noisy image, a foggy room, and figuring out what's going on in that foggy room. And so that ability to do that has revolutionized potentially video games in that here is a ray traced image. Ray tracing is the ultimate technique for generating images. This is what Hollywood uses for CGI effects, but it's very expensive. So Hollywood uses big rendering farms and will spend days to render a few seconds of an image. The idea of doing ray traced images in real time was kind of science fiction, let alone doing it on video game level hardware. However, a couple of years ago, people were amazed when all of a sudden Microsoft and some others said, hey, we're going to put ray traced video games in our next generation of consoles and some upcoming video cards. And the reason they could make this incredible leap forward was they trained a network to recognize these noisy ray traced images that are in some sense low resolution, 1 ray per pixel, and be able to reconstruct out of it what's really the room really looks like in high resolution. Again, it's like you walking around in a foggy room. You eventually realize what the room's supposed to look like, and you don't get confused because there's a little bit of fog moving in front of that bookcase. You remember there's a bookcase there. Recurrent neural nets can do that, and they can do it in real time. So once you train that recurrent neural net, you can stick that, because we know inference is very lightweight and fast, you can stick that then in an Xbox or on a graphics card. The latest NVIDIA graphics cards all have this capability built in to do this real-time ray tracing because they have little tensor processing matrix multiply engines built in as special hardware. So that's interesting because it's just revolutionized in a couple of years from science fiction to potential consumer product. A little bit more in the science world, we are now incorporating neural nets into very physical sciences where it seemed ridiculous before. I've had a friend who's one of the world's foremost numerical simulation people, and he summed it up what I thought was a quite true thing. He said, John, I don't need neural nets to rediscover conservation of energy. In other words, saying neural nets have to learn stuff about physics. We already know how to plug into physics. It's ridiculous to think that they're going to be good at that. And I agreed with him 100%. This is about 10 years ago when we both were starting to get distracted by neural nets. Now, however, we find that we were both a little bit mistaken. We both underestimated how effective neural nets could be at learning incredibly complex physical equations and somehow extracting the physics out of them. Here's an example of a flame front, which is multi-physics at its most. It's got chemistry, thermodynamics, fluid dynamics, all this stuff going on. And yet this neural net learns to predict fluid flow pretty far out in time, in some sense, for chaotic flows. It's learning how to do all of that physics with a neural net. We've seen some demos about combining style and content together. They are very much capable of being photorealistic with code that you can understand very easily right now. So you can grab the code and be able to fake completely, turn a summer scene into a fall scene. So this kind of stuff is frighteningly effective. Probably if we were to go into tomorrow, day 3, I might jump onto this project right here, generative adversarial networks, to generate new and interesting scenes. There's a nice video of what they're doing at this site, but briefly what they're able to do is create completely new faces. None of these people actually exist in the real world. These are all network generated. And they do it with that generative adversarial technique I showed earlier. Saying none of these rooms exist, none of these cars exist. These all look like plausible cars, but if you know cars, or if you don't know cars and go searching around, none of these car models ever existed. So these are all strictly from the mind of a generative adversarial network. One piece to take away from this paper, if you go read the paper, you'll understand the pieces that make up the network. Maybe not all the details, probably not a lot of details. But one of the things to take away is they really talk about their hyperparameters that they're using here, where they use, batch norm. They don't use batch normalization, blah, 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 dropout, what they use. But most importantly, you get an idea that the hyperparameter search was a huge part of this effort. So it's not at any point in time we realized that we should use this feature because we're geniuses. Instead, hey, we had to do a lot of testing and trial and feeling about to figure out how this network should be put together. And that's the most sophisticated stuff going. Okay, with that, we are not only out of time, we're over time here. I'll answer the last couple of questions here before I make sure to do the most important thing of all, which is to thank the appropriate people and tell you where you can go next for startup grants and whatnot. Let's see, possibly use libraries from Bayesian optimization, Gaussian process regression with bridging. Yeah, sure, absolutely. There are, as a matter of fact, I think some of those are at hand in Spark. And thank you for your thanks there. And let me return that because I'm thankful for your time and attention here. You are the reason we do these things. And I want to make sure that you in the future, again, have access to these resources. Some of you may be interested in this even, which is the fact that there's a digital badge with this workshop. You should be able to easily pass this digital badge. So if you'd like to earn an Exceed Big Data digital badge as credential, please go ahead and take that test. I think you'll do well at it with what you know now. Please fill out the post-event survey. We really take your feedback seriously. We've done an awful lot of new material, maybe too much this last session here, but your feedback tells us what we should do, what we can do, what we should cut, what we should add, whether this format, particularly this is our first time of doing this in Zoom instead of the wide area classroom. I definitely feel like we were a little bit of a handicap. I regret not having as much interaction with you. I do miss that. I think we did the best we could with chat and whatnot, given our class size, but I welcome your feedback and your criticism. Please let us know where we fell short because this is a little bit new to us. We don't know where the gaps were, and it'd be nice if you let us know and gave us some feel for it. And that will let us improve, especially if we are forced to accommodate and stay on Zoom for a while before we go back to the wide area classroom. And I guess that is it. Okay, well, let me officially thank you all for your time. Again, if you do something exciting with this work, we're always very happy. I'm in particular delighted to hear about it. Please let me know. With that, I will let my team go. They've been, I know, stretched their patience there. Thanks for sticking around, guys. Normally, the wide area classroom will cut us off physically at 5. I took advantage of the fact that the Zoom, I guess, gives us a little grace period here. So thank you all. Thank you, production team, for doing such a good job here. And I guess Steve can shut down the Zoom session and resume his life. Can we get a grant just to check it out? Yes, you can. That's what a startup grant is, just to check it out. Go ahead and get a startup grant.
So John, did you want a copy of your individual chat? You probably didn't do much individual chatting, did you?
No, I didn't, but I would like a copy of the general chat so we can see if we overlooked anybody in the flurry or whatever. So please grab a copy of this.
All right. And with that, I think we'll sign off. I want to thank everybody for coming. Thank you, John, very much. You did a great job. Hope to see you all soon.